So in terms of soils, again, amazingly complex, and we could literally teach an entire class, the entire semester on this topic. So necessarily then we're going to try to, hit the highlights. One of the things that we need to first start out with in recognition is that soils take a long time to mature and to develop. How long? It depends. There are things called recent soils, and I'll tell you the name about those later. You don't have to write that down because there's actually a more technical name called an entisol, which basically means a recent soil. Those can be types of soils that form in just a matter of days, actually. But then you may have soils like a mollisol. Again, you don't have to write that down. I'll come back to it. That may take tens of thousands of years to form. Okay. Now, as soils mature and they form over time, one of the things that they do is there's lots of processes at play here, right? Just think about what's happening down under our feet. You got rainfall operating. You've got freezing and thawing and contraction of certain kinds of soils, like when it gets cold. What are some other things? Talk to me. What are other things that affect the soil underneath your feet? Got bacteria, right? Let's keep it going, Chase. Absolutely. Chemical reactions, fungi, natural disasters. Give me an idea of one, maybe. Tornadoes, okay. Got flooding, yeah. Juliet, earthquakes, great. Landslides, okay. Lots of stuff, right? So both biological impacts, we mentioned hydrological changes with water, right? Flooding, natural disasters. What are a couple things we did not mention in that list? Other major groups.
Pollution.
Yeah, human impacts, right? Compaction, right? Buildings and debris and things. I think Laura said pollution, right, Laura?
Yes, I did.
Excellent. Yeah, right. You can have all kinds of forms of toxin buildups in soils, right? Tilling and farming, exactly. Think about natural processes now. What are maybe two key groups of natural processes? Maybe one was mentioned, I can't remember, but let's think about two big categories. We said bacteria. That's sort of getting there, but not quite. We said fungi. What's one? All right, so plants and animals, right? You've got obviously root systems penetrating the soil, right? And growing and fracturing and the decay process, absolutely, especially through fungi and bacteria. What other kinds of biological effects on the soil do we have? The tunneling by things like what? Yeah, right. So bioturbation is the term for that. When you have plants and animals that are churning the soil and creating that sort of, that churning effect. All right, one more key factor. We might have hit it loosely, but I want to just make sure it gets spoken. What else?
Mineralization.
Yeah, certainly minerals, geology, that all definitely plays in. One more, I'm gonna give you one more chance. If you don't say it, I'll say it.
Evaporation.
Nitrogen fixation through mycorrhizae. Laura?
Evaporation.
Ah, you're touching on it now. What is evaporation connected to, Laura?
The transpiration, like moisture coming up out of the soil and carrying the salt to the surface.
What's that broad term to encompass all that stuff?
I don't know. I don't remember.
Jacob? Humidity, but what term broadly encompasses humidity and temperature and evapotranspiration? The water cycle, still encompassing all that is climate, right? Climatological impacts, right? So all those things help shape the soils that we're looking at. Now, a typical soil is going to have some expression of layering, right? Especially those that are old and mature. So you might expect to see these different layers, and sometimes these can get very complex, and you can have much more than this simple arrangement that you see here, right? Typically, you have an organic layer at the surface that's called the O horizon. And this consists of loose and partly decayed organic matter. You don't always have that. It just depends on the soil type. But here you obviously can tell it's rich in organic matter in the top profile of the soil because there's a lot of dark blackish or dark brown coloration. What that means is what can you infer is present when you see those dark colors like that, the blacks and the browns? Minerals, particularly I'm thinking of one element in particular. Carbon, exactly. These are carbon rich. This is a big topic right nowadays with carbon sequestration and trying to mitigate climate change. One of the theories is if we can draw more carbon into the soil out of the atmosphere, then that could be one way to tackle and help offset climate change by more fossil fuels building up into the atmosphere. So things like grassland restoration, prairie restoration, right? You're trapping more carbon into the soil through those processes. As opposed to say, if you're tilling everything and plowing everything, more of that carbon is being released, okay? Now, beneath that O horizon, you have what's called the A horizon. And this is that top layer. It typically is dark in many soil types, but again, it depends on the soil. And this is what we would typically think of as topsoil, right? If you're planting a tree or burying a dead pet, you like the topsoil because it's kind of the easy part to dig in typically, right? But what happens when you get down about 10 inches or 4 inches in some cases? You often hit that clay layer that's very difficult to dig through. And that then begins one of these lower layers. Sometimes you go straight to what's called the B horizon, which is your subsoil. That around here is oftentimes sort of a reddish clay, and it's just not fun to dig in. And the drier it is, the worse it is. You can have another zone in there, which is very light colored because of leaching, where the minerals have sort of drained out of it down into lower layers. And that's called an E horizon. And then finally, as you get farther down into the sequence, and you can see that over here as well, here's that E zone right here, right? Here's your topsoil. You've got an organic layer up top. This is probably getting into your subsoil here. And then notice you start picking up a lot more rock fragments. Okay, as you approach deeper and deeper into the soil, you're getting closer down to what's called bedrock, and that is the parent material. So limestone bedrock. Weathering of that limestone, notice how it's beginning to fracture. You know, maybe that's acids and rainwater fracturing that. Different root systems of oak trees may penetrate and help fracture that. Ice. All these things help to fracture that, breaking it up. And gradually, those top layers of bedrock become more and more fractured, and those rock fragments tend to work themselves up. And what else is in that rock, right? What's in sandstone? What's it primarily composed of? Juliet, what is sandstone made of? Sand, right? Which we could simplify and say, well, sand is made up of like the mineral quartz, right? But you can picture a sand grain. So sandstone weathers into sand. Limestone weathers into clay, okay? And we're going to talk about some of these other kinds of things. So that gives you an idea of what happens when you take the bedrock and you begin to weather it and break it down. What's kind of happening in these layers above? If you weather sandstone, you can expect very sandy layers above it. That's being derived from that parent material or that bedrock. If you're weathering limestone, you would expect this to be very, very clayey soil, very hard to dig through, okay? So these are the basics of a soil profile. What do I want you to know? I would like for you to just know the basics. I mean, this is almost like kind of about middle school level, right? You need to know the O and the A and the E and the B horizons. And then generally that they are all sort of derived from this parent material. I just want you to be able to know the basics there. As I said, there's a lot of things that are contributing to soil formation. And we talked about some of these. So there are additions of various types of things to the soil. So you have water that is precipitating through from rainfall or groundwater. You can have condensation. You can have runoff of various types of things, oxygen and carbon dioxide from the atmosphere. You can have a buildup of nitrogen. right? Think about if you add fertilizers to the soil, right? You can have various kinds of other elements. Organic matter from plants that are building up. All these things are additions to soil, okay? You can have other types of sediments. Maybe you have erosion being washed down from an adjacent slope. And you can even have high intense sunlight, solar radiation, which can affect the soil. And then you can have losses from the soil. You can have evapotranspiration, where water is being lost from that system. Nitrogen can be lost through denitrification. So sometimes if you grow corn on a given crop, a piece of land for too many years in a row, it depletes that soil of nitrogen. So what do farmers do? Anybody know? You rotate out and you plant it with some type of bean, like peanuts or soybeans, right? You usually put beans in for a year or so. They have nitrogen fixing bacteria that work with the mycorrhizae of their root systems to replenish nitrogen to the soil. You can have carbon as either carbon dioxide or other types of forms that can be lost from the soil, especially through things like plowing. Erosion can take away. And again, there's energy transformations as well. And then you've got other kinds of things that affect it, but I just want to hit the highlights on some of these. You don't have to memorize any of this stuff. I want you to just think about the fact that soil is dynamic. It's gaining and it's losing stuff all the time. Then we talked about how there are really kind of four major elements that are affecting soil formation. We talked about climate, things like temperature, soil temperature, soil moisture, topography, which gets to landform. You know, are you on a hill or a mountain or in a valley, on a plain? What type of parent material? That's directly related to geology, right? The bedrocks. That's why we start with geology in this class. And then what I love is kind of why I had Theo speak on this today is all the plants and the animals that ultimately can be tied back to that specific soil type. So the biology matters. We mentioned a few things like earthworms and moles. And here are some things that help to churn up the soil or turn it over. Crayfish actually do have a dramatic impact on soil bioturbation, or this turning over of the soil. Did you know that one of the properties of an old growth forest is that they have really complex soils that happen to have a lot of underground burrows and chambers? And that's one of the hallmarks of an old growth forest. So if you look at definitions by the old growth forest network or the U.S. Forest Service, they have like 12 definitions or so that make up what an old growth forest is. And that's one of them. They have a lot of underground burrows and chambers that help add to the antiquity of that ecosystem. This is one of my, Theo's, who's on here, of course, has studied this a lot. This is one of the few endemic mammals. What is that? What do we mean by the word endemic? Just only in one spot or one localized region. And this is called the Ozark pocket gopher. And what's really cool about this is you can see here, this is someone's field, pasture or something out in northern Arkansas in the Ozark Mountains. And you've got these mounds here. And to someone who's walking out there for the first time, like if I had gone there, I would have probably from a distance thought, hey, y'all be careful. Watch out. Don't step over there. What would I be warning my children about stepping out here?
Fire ants.
Fire ants, right? Because they build big mounds like this, right? And I'd be like, Maddie, get off that fire ant mound. You're going to get bit, right? Well, in actuality, it plays on my fears of rodents. I'm hugely afraid of rats, by the way. But this little critter is cute, right? This is the Ozark pocket gopher. And so it burrows here, but it's only able to do it because this is a pocket of very specific soils within an otherwise part of Arkansas that is very rich in limestone. But here along these select river valleys where you have these sort of sloping terraces, the soils are really sandy. The adjacent uplands have a sandstone bedrock. You can see some of those cropping out. And that contributes to this unusual concentration of sand in one county or so in Arkansas. And I'll show you the map here. So this is Stone County, Arkansas. I guess it's in all four of those counties. Is that right, Theo? This thing's in all four counties or just in Stone?
No, Dwayne, that's Izard County, and it's only known
Hmm.
from a small part of Izard County.
Yeah, well, I
Um,
got that other map somewhere.
Well,
Totally.
okay, so I think there was some possible old report from Stone County just over the
Hmm.
line, but they've never relocated.
All right, but the one that I've got shown here with the dot and the close-up map on the right, that's Izard County.
That's Izard County, and that dark black line there is about the range of that thing, right?
Okay. This is the total global range, and you can see from this topographic map, these are relatively level uplands, sort of a plateau up on the north end of the county. There's a couple of river valleys or river down here. I guess that's the White River, right, Theo, on the southern border of the county.
Yeah, that's the White River.
Heavily
And
dissected.
these valleys are tributaries that flow into the White, but they're small creeks compared to the
Small
river.
creek
Yeah.
valleys there, yeah. And so in this heavily dissected landscape with these small valleys, you have this endemic mammal that most people don't even know about, right? It's just fascinating. But it wouldn't be there without these really heavily sandy soils that, again, they really matter with particular species. So, secondly, in addition to the biology, obviously the parent material matters, and that's again getting right back to geology. So, we're gonna hit the highlights on how these different kinds of rock types matter when it comes to soil formation. And we can take a look here. This is a process that takes a lot of time. You can think about some sites maybe undergoing sort of new in that process. They have immature soils where that the parent rock is just barely weathered at all. Maybe got a thin mantle of soil on top of that. Then you've got progressively with time on this axis, you get more and more sort of accumulation of organic matter as that bedrock is sort of breaking down. Sometimes we call that rotten rock, where the rock becomes real fragile and brittle, sort of begins to break apart. And a lot of things are contributing to that, right? You got organisms that are contributing to that, and various kinds of abiotic factors, and things like root systems, which are breaking that up. And then progressively, you've got more mature soil with time. And here, this just sort of summarizes some of the things we called out earlier, like bacteria and fungi and millipedes and earthworms and all the plants at the surface and the trees and the rocks and the soils, all contributing underground with these underground sort of networks to help in the process of soil formation. This little diagram on the right here just sort of visually and very simply illustrates what happens though with different kinds of rock. So take granite, for example, this rock right here. With this rock, as we passed around, some of you were out, maybe at the restroom. Remember, there are two basic kinds of igneous rock based on their, well, it's not that simple. Two of the major groupings we talked about based on, if it has really light colored minerals or grains, crystals, we said that those rocks are called what? Felsic, and those that have a heavy concentration of dark are called mafic, right? So see how light that rock is? Just peppered here and there with a little bit of dark. Those dark are the black or mafic minerals, and these are the felsic minerals. Felsic igneous rocks tend to be have what type of pH? They're acidic, okay? So we can begin to look at something like granite with some of its very basic mineral components. So like feldspar is one of the minerals. Again, I'm not going to require you to know minerals, right? But I want you to conceptually understand what I'm talking about. Feldspar, as it weathers into clay particles, okay? So as this granite piece breaks down as parent material, as it begins to break apart, those felsic minerals, those like feldspar, will eventually form clay-based soils above it, okay? And then you're also going to have some other minerals in here. These are often the ones that are kind of whitish colored in granite. These are your quartz minerals. They can be sort of beige colored. Those often, because they're formed of quartz grains, those are the basic sort of mineral that forms up sand. So those become sandy. So granite soils tend to have sort of a mix of both some sand grains in it as well as some clay-based particles. And of course, it matters what else you got around, right? If you have another rock type like sandstone that's also eroding away, maybe it's contributing more sand than just the granite does. If you have limestone over here, it's contributing more clay. All those things are impacting what the ultimate composition of that soil type is, whether it's a clay soil or a sandy soil or kind of a mix of the two. Now, as we think about soils and how they're forming from this parent material, one important concept is just how deep are the soils, right? Because we do have whole ecosystems that form where, maybe it's an outcrop on a mountain. It may not have any soil except in the cracks where the pocket, like these little holes in the bedrock occur. You may have these little soil islands, for example. And so lots of ecosystems like glades and barrens and outcrops or cliffs have almost no soil or very shallow soil. So it's important to think about just the general importance of root depth here and how that dictates what type of ecosystem you have. The shallower it is, the more you expect it to be dominated by grasses or herbaceous plants. As it gets deeper and deeper, you expect shrubs and trees and those kinds of plants with larger root systems. Now, bigger trees and stuff like that don't always mean deeper root systems. One of the things we've seen from the Great Plains, for example, is that a lot of your tall grass prairie plants, many of which we have planted out there in our botanical garden, can have root systems that are way deeper than your typical tree. They can go down, in some cases, 30, 40 feet deep and tap into groundwater. Much, much deeper than, say, crop plants or shrubs or trees. But importantly, if you do have a restrictive layer due to rock, it can restrict tree growth, and that can force it from going to otherwise what would be a forested ecosystem to one that is a grass-dominated ecosystem. So there are some general descriptors, and a lot of what you'll see in this PowerPoint are these categories that the U.S. Department of Agriculture has come up with to help sort of classify these general. So we have soil depths that range from very shallow to shallow, moderately deep, deep, or very deep. Very much intuitive, right? This is what it looks like on the side, where you can have a range of different rock types as well. Now, another key point as we're putting all this immense amount of information that I'm throwing at you guys in this class is there are different terms for different kinds of, not only the kinds of rocks, right? The different geologic types, but we also have terms that affect rock sizes. Well, of course you do, Dr. Estes. I wouldn't expect anything more than just some more terms. Again, I'm not requiring you to memorize all this stuff. I want you to think about it conceptually, one, and then I want you to see, and I'm going to show you as we go through this class, everything we're doing is going to build on itself. So when we come, for example, later and we talk about stream systems, that's where I'm going to come back especially and build on this. Like, why do you get a gravel bar in a certain place? Why do you get a sand bar in another kind of place? Why would you expect a block field to be on a mountainside and not in a floodplain, right? So don't worry if you don't get it now, because I'm going to hit you with it about 3 or 4 times through class. Clayton? Pararock. I have no idea, honestly. I'm just going to tell you, I've never even seen that term in my life. So, and I reasoned, because there was lots of terms I was like, I don't know what the hell that means. If I don't know it after 45 years of living and 10 years of schooling and 17 years of teaching, then by God, you don't need to know it either, okay? Unless you just want to know it. Is that fair enough, Kim? Yeah. All right, so what's the key point here? Number one, just think about this. For most kinds of rocks that we would see out on the landscape, you need to think about things as generally on the small end, pieces of gravel, right? If those gravels are sharp edged or sort of smooth, that's going to matter. It's going to tell us how they were put there, whether they were put there by water or a landslide, those kinds of things. And there's all kinds of levels of gravel. We don't need to get into all the details of that. The key thing here is gravel, cobbles, and stones and boulders. Just looking at the general size class for those. So gravels are pretty much anything that are up to about 76 millimeters in diameter. Cobblestones, I just generally think about cobblestones as being anything that's sort of like almost up to head high, head diameter or smaller. Okay, these are cobblestones. Stones here are on the bigger end, and then boulders are much bigger than that, so 600 millimeters and larger. All right, just for convenience purposes, I've kind of arranged these, and you can also then go from the very biggest, say them with me, just so we can kind of have a little repetition here. Boulders, stones, cobbles, sometimes called cobblestones. All right, gravel, sand, silt, clay. Okay. Why does it matter? Here's why. Imagine that erosion is happening in the Rocky Mountains. Okay, raise your hand. Anybody been in the Rockies? A couple of you, right? It could be any mountain range. All right, you're up on the side of that mountain range, and erosion is happening. Wind and water, gravitational pull. There's a process called mass wasting. You know what that is? Just when the force of the weight of the rock causes it through gravitational pull to fall, oftentimes driven by things like earthquake activity, right? Earthquakes can shake rocks loose. Or we came through a very cold spell. You ever drive down the interstate in the middle of winter when it's very cold and you see that the cliffs are hanging with icicles, right? If you'll watch after a real cold snap, if you'll notice at the bottom of those cliff lines, those artificial road cuts, they will be full of rock debris at the end of winter. All those rocks, basically, every time those cliff faces freeze and thaw because there's water trapped in those rocks, it causes the ice between the layers of rock to expand. It pushes the rock face out and it breaks off a face off the rock. Then it breaks those particles off, and then they just accumulate right there at the base of the roadside on the interstate. In fact, sometimes if you watch, there'll be people that actually stop and will be shoveling that rock up. I've done it myself, even though it's illegal. They don't want you doing that. In fact, one time Channel 4 News had, "Are you guilty of pulling over on Tennessee's interstates and scooping up rock?" I was like, yeah, that's me. In fact, a lot of the rock in our garden came off the interstates just the same way, me and my grad students. So imagine then that rock is falling off a cliff face. Boom, 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 giant, size of a living room, right? Tumbling down, doom, 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 boom, boom. Gravitational pull, wow, falls into a ravine at the base. And it's there for thousands of years. Imagine all the force that's needed to break that big house-sized boulder up into smaller fragments, right? Enough to get down into the range of a small boulder. Well, then typically other actions like landslides have to carry it farther down the mountain, right? And then they break up some more over thousands of years. And then they gradually break up through freezing and thawing. And they break up and they tumble and they tumble. Then maybe a river carries it 100 feet. Quick story. On the Cumberland Plateau, about 3 hours east of here, we were doing some projects about 10, 15 years ago. And the National Park Service wanted us to survey these river canyons, like these box canyons. You get in, it's a flash flood, you better get out, right? It's that dangerous. Water levels can go up instantaneously, can be not raining where you are, and you can have a wall of water because it's raining 20 miles upriver, right? It can come down and kill you. In these types of canyons, the riverbed is choked with these massive boulders. And I started wondering to myself, I was like, can these things actually move? And I was with a park ranger who said, you betcha they can move, absolutely. He said, not the biggest ones. You know, they have to be broken and they pretty much fall down and boom, they stay put, unless something breaks them apart. But he said, you know, these that are the size of like a bathtub or, you know, maybe even 5, 6 feet in diameter, some of those can move. I said, you're kidding me. He said, no, I'll tell you what, I'll tell you a story. He said, about 20 years ago, I was out here. This is the Obed Wild and Scenic River. He said, we had, you know, 15, 20 inches of rain over a few days. The highest flooding I've ever seen in that canyon, you know, water was pouring down 150,000 cubic feet per second. The water was 40 feet high. It was just dangerous. And he said, I walked out this 2-mile trail out to the top, and I looked down, and this violent river is crashing. It looked like the bottom of Niagara Falls, right? And he said, and you could hear it, click, 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 as the boulders were popping into each other, as they were being pushed downriver. So these boulders, which our story here is beginning with, some of them can move, right? Through things like gravitational pull and even the force of the water as they get smaller and smaller. Then they break into stone-sized fragments that can move even farther. Now, I want you to think about this, right? We're starting in the Rocky Mountains, correct? So these boulders, how far from the Rockies can they move? They can't. They cannot leave the Rockies. Imagine you emerge from the mountains. The boulders stay in those mountain streams. They choke those river canyons. They never can be carried farther away because it's too far to go, right? But what about the smaller pieces? The stones. They also don't get carried out of the mountains. They're too big. They can never be carried dozens of miles away or hundreds of miles away unless something massive and unexpected happens, like, you know, a tsunami or the breaking of an ice dam in the ice age. What about cobblestones? Head-sized pieces of rock are smaller. You know, a softball, a grapefruit size. They can move, they can be transported a little bit out of the mountains. In fact, if you ever go to places like Gatlinburg or the Smokies or places like that, if you'll find where a river has come out of the mountains and you look into the soil profile, you'll see cobblestones usually down in the side of the riverbed that have come out of the mountains a half a mile or a quarter of a mile, maybe even a mile. So cobblestones can be transported. Now, let's come out, let's leave the mountains behind, and let's come on down onto this area below the mountain range, looking out into the distance. Let's follow that riverbed down. Let's explore it like we're Lewis and Clark in the old days. We're stepping on the cobblestones, and because they're so big, it's like stepping on basketballs. It's hard to walk on, right? Finally, gratefully, we get away from the cobblestone zone. We get into the zone of smaller rock fragments, farther away from the mountains, that's gravel. Now we have gravel beds lining the rivers. The species that live in the cobble areas, in the boulder areas, and the gravel areas are all very different from one another. These rocks matter to biology. They matter to the species. But we haven't got to the smallest particles yet. We keep going on downriver. Now we're in eastern Colorado. We're making our way across the Great Plains as the Arkansas River has come off of the Rocky Mountains, or the Colorado River has come off the Rockies. Where are they ultimately, those two rivers going? Coast of Texas to the Gulf of Mexico. That's a long way to go, right? So we get through into parts of West Texas and Western Kansas, Western Nebraska. Those rivers have gravel bars along their streams. Then we get too far from the Rockies for even the gravel to be transported. And then what begins to drop out and form the dominant bars along the river's edge? Sand. We get sandbars. Those sandbars carry far and wide. They get reshifted, and floodwaters take them even farther. Then they move even farther. They make it all the way down to where they enter the Mississippi River. And then they continue. And sand goes all the way down into Louisiana, into East Texas. And along the way, silt, right? Think about the floodplains of the lower Mississippi River Valley. What makes it so fertile as a region for growing cotton, corn, soybeans. All those silted floodplains, that's because the silt was ultimately carried from places like the Rocky Mountains, transported thousands of miles, suspended in the water. You ever see them, like right now, if you look at the floodwaters, they're laden with brown silt. They're carrying silt. They're carrying two particles, silt particles that are 0.002 to 0.05 millimeters in diameter. And they're carrying clay particles that are less than 0.002 millimeters. Okay. Now, Imagine then that river floods its banks, and that brown water goes out and suspends over. And what happens? That silt drops out and drops onto that new floodplain. That's one of the things that replenishes that floodplain and makes it more nutrient rich, right? It makes it great for agriculture. Now, what keeps going all the way out? All the way out the mouth of the Mississippi River, carried into the Gulf of Mexico, into what's called the Gulf of Mexico anoxic zone. You know what that is? It's the zone where there's so much pollution now that it's an oxygen poor zone right off the coast of Louisiana. It's crippling the shrimp industry. It's harmful. It's polluting, and it's in those zones, you know, a couple hundred miles out to sea, that the smallest particles are carried, clay. And guess what they're doing? They're dropping out of the Gulf of Mexico, beginning to suspend, and they float to the bottom, except there the Gulf of Mexico is not 100 feet deep or 200 feet deep. In some cases, 300 or 400 feet deep, or 500 feet deep, or 1,000 feet deep. And these clay particles are just dropping and building and dropping and building and dropping and building. What I've just described to you along the way are different what? Depositional environments. And those depositional environments, whether it's an avalanche at the base of the Rockies forming breccia as rock formations, as it forms in the rock, or those sandbars on the banks of the Arkansas River form eventually into sandstone, or the clay particles that go out in the Gulf of Mexico eventually form into marine shale. Now, all this is exceedingly important for two factors. One, we want to be understanding of the role that these sediments play on the land because of how they influence biology and ecology. But we also want to be understanding of how they end up getting deposited, because that is what will tell us about geology and the long-term changes of Earth. Because one of the things we're about to get into soon is these massive level changes of the landscape and how that ties into the fossil record. Okay, climate's real important. For example, here in Alaska, we can look and see that below this fairly shallow soil that's mostly dominated by grasses and mosses and stuff, if you get down about 6 inches or 8 inches, you hit a what? You hit an ice layer. And that's because this has a permanently frozen subsoil called permafrost. And I know what you're saying. It's like, man, why is he teaching us about stuff that's up on like Ellesmere Island, Canada? Like I care about Ellesmere Island. You know, what's happening in Greenland ain't affecting me. Well, don't be so sure, my friends, because although Tennessee has never been covered, well, not at least in the past, you know, probably 800 million years, has not been covered in a glacier. We did have permafrost at one time. And I'll tell you about that. So why does this permafrost matter? Well, as we start talking about global climate change and the movement of species over time and things like biogeography, it helps us to be aware of even key differences of like where the tree line is between the tundra and the boreal forest, say in northern Canada or in Siberia. If you look at this map on the left, this is tree line all around the world, through Alaska and Russia and all the way up through Canada, Greenland. And above tree line, above the Arctic Circle, is a permanent layer of permafrost that prevents the growth of trees, very much like how a hard pan in Arkansas would prevent the growth of trees, or how bedrock glade in Tennessee would prevent the growth of trees, right? So you get above that zone, you have too shallow soil over that frozen subsoil. But we didn't have to go so far north that long ago. Just 18,000 years ago. I know what you're thinking. My gosh, he's digging far back. That's a long time ago to me. Sounds like it. Yeah, but get this. 18,000 years ago, there were people, human beings, walking around in North America. Fascinating new study from New Mexico, a place called White Sands National Monument, has documented human footprints walking nearly alongside extinct giant ground sloths. walking in proximity to extinct saber-toothed cats. All of these were walking together on these open lake shores 21,000 years ago. So what was happening here in Tennessee and Kentucky 21,000 years ago? Well, we had a massive ice sheet that, like you find today, covering Greenland, that covered all the way down to almost where the Ohio River and the Mississippi River come together. So places like Paducah, Kentucky, were just south of the tundra zone, right? Paducah is like less than 2 hours away. You know, Carbondale, Illinois. Any Illinoisans in the room? I had 3 last class. So I had 3 Illinoisans. But yeah, Illinois was kind of in the center. So this black zone that you see here was the tundra zone along the ice front. And I want you to notice how it went from Massachusetts, and here's New Jersey, across Pennsylvania, down through Ohio, right? Cleveland, Ohio wasn't in the tundra zone. Cleveland, Ohio had 5,000 feet of ice above it 18,000 years ago. New York City had 2,000 or 3,000 feet of ice over Central Park. Chicago had a mile of ice on top of it, right? But south of that, all the way over to St. Louis was in tundra. What about Tennessee? You still ain't told me about Tennessee, Dr. Estes. Keep talking about these faraway places. Ellesmere Island. And what to think about that. So what do you think? Any tundra in Tennessee there based on what I showed you? What do you think? Sarah? Any tundra? Kiki? No, doesn't look like it. All right. What do you think, Chase? Those black patches coming down? Yeah. Yeah, black's tundra, right? And then notice it does this funny thing. What is that? What's the tundra is following the tops of the mountain ranges, coming down the Great Smoky Mountains and the Blue Ridge Mountains. So places like Shenandoah National Park and places like Cranberry Glades in West Virginia, or Roan Mountain and Great Smoky Mountains National Park, all those would have been within the tundra zone. Raise your hand if you've ever seen the Smoky Mountains, okay? Researchers think that about the top half, roughly, of the mountain range, if you were to look from Knoxville or Gatlinburg to the mountains, about the top half to maybe the top 40% of the mountains would have been enveloped in tundra 18,000 years ago. What would have kept it as tundra? Well, we didn't have glaciers, but we had frozen soils that kept the tops of those mountains in tundra and dominated by grass vegetation, grassland vegetation. Okay? So climate has a big effect. Now, so climate obviously then can affect things like temperature zones. And I don't know if you guys saw this just about a month or so on the television. There was a big announcement. It was on CNN. It was on like Channel 4 News, et cetera, that we have shifted in what we call our hardiness zones. Anybody see this? Y'all see this stuff? Yeah. So why does this matter? Well, here's why it matters. Because let's say 20 years ago, if my grandmother wanted to have planted a magnolia tree in north central Tennessee around Clarksville, she'd be like, well, I don't want to plant a magnolia. Your Uncle Larry gave me a magnolia, but I don't want to plant a magnolia up here in Clarksville. Why not, Granny? Well, don't you know, Dwayne, magnolias only grow down there in Florida and Alabama. Well, they're not going to grow here. It's too cold. Well, Granny wouldn't be saying that today, God rest her soul, because the temperatures are warming. Well, Granny. Exactly. Be proud of the gift that Uncle Larry gave you. So the soil temperatures are part of that, as well as the ambient air temperatures, right? So this is showing the general areas of soil temperature. And you can see, and I apologize, this legend, I swiped it off of Google Images, not very legible. But we're in a zone here called the thermic soil region, which basically means warm soils. Farther north you go, you get up in that blue area, those are frigid soils where they're very cold. But here's those hardiness zones. So at the time that Granny wanted to plant her magnolia, back say 20, 25 years ago, we were actually in a different climate zone. Notice that today, this is only up through 2005. So this is probably the zone under which Granny had planted her magnolia, right? Let's say she planted that magnolia there and she's in this zone of light green, okay? I think that's zone 7A. Here what we have is the minimum temperature in Celsius and sort of the minimum temperature there in Fahrenheit. About the lowest you expect is kind of what we had last week. Remember, it was in 2 degrees, 3 degrees, 4 degrees. If it stays above that for too long, it will kill things like southern tree species, for example, like magnolias. Well, what we've now noticed in just the past month or so, the U.S. Department of Agriculture has totally reclassified this based on climatological data. Long-term trends have shown that Middle Tennessee now is no longer in zone 7A. That these latitudinal or sort of these cross bands have actually shifted northward based on climate patterns. We're now, I believe, in 8A here. So we're now in a zone that climatologically was like Birmingham was 20 years ago here in Middle Tennessee. And what we might possibly anticipate is, for sure, we are already seeing a dramatic increase in the number of 90-degree temperature days in the summer. But things like the minimum lows in the winter will also be potentially affected. So it'll matter to agriculture, it'll matter to biology and ecology as these things begin to shift. And of course, one of the things that's impacted relevant to our lecture today are the soils themselves. Clayton?
I've only ever looked at the eastern half of this hardiness zone map.
Yeah.
What is going on in the west? Why do the bands contribute?
Right. So out west, obviously you have the Rocky Mountains, right? And then you've got the Sierra Nevada mountains, which are contributing to sort of this degree of blue here. And then you've got all these isolated mountain ranges in the Intermountain Basin region. And then within that, you have rain shadows. And all these sort of have they affect the airflows and the temperature patterns. That high degree of topographic complexity is what's breaking it up. Here, the only thing you've got is one range of mountains, the Appalachians, and it allows you to have this sort of wide, continental wide sort of climate type. Now, one last thing here is soil moisture. Now, this is a very coarse map. It's impossible to show you the fine scale details. And to Clayton's point, you expect, and this is what you see. Notice how homogeneous the eastern U.S. is in most of these things, like temperature patterns, soil moisture patterns. Lots of heterogeneity in the West. And that's because of the complexity of geology and landscapes of the Rockies, similar to what we talked about earlier. Now, one other factor here is the distinction between sort of these general moisture regimes for soil. So do you have a super wet soil that's constantly waterlogged? In that case, then, it is referred to as an aquic soil. So lots of these are found in places you would expect, along the coast, right? Up around the Great Lakes. This area, for example, of Northwest Ohio used to be a massive marsh system. So naturally, those soils are kind of aquic and along the Mississippi River floodplain. The other ones here, largely just kind of broadly across the eastern U.S., are referred to as eutectic soils. These are not continuously wet and waterlogged, but they're also not like desert soils, right? Like the eritic types that you see out here, all these reds and oranges and yellows make up very arid types, like you would see around the Sahara Desert or in other desert regions of the world. So very broad categories. Soil moisture matters, soil temperature matters. That's really the only point I want you to remember from that. Okay. Now, this does not mean that there are not wet soils in here, right? This is generalized patterns. What I mean by this is imagine that if you were to walk out and look at the landscapes, let's say flying over an airplane in Tennessee, 90% of the soils that you see are generally moist to slightly moist, maybe a little dry. They all follow, all 90% of them fall into this Utic category. That doesn't mean you don't have a wetland in the middle that's an actual aquic soil. You do. It's just they're dotted, right? And so this is showing general trends. Versus if you're down here, the predominant, like the majority of soils are aquic. The minority would be Utic soils. So you do have upland soils, right? Think about it. Miami, Florida is an upland city on the coast, right? They have to be. Otherwise, you can't really build easily in a wetland like that. So you do have these pockets of uplands in those areas as well. This is sort of generalities. All right. Now, without getting too complicated, I just want you to sort of be exposed to some of these soil moisture regime types. And the one I want to focus in on here is kind of probably the one most relevant to us is this one in the upper left. Okay. You'll commonly see these kinds of diagrams related to climate patterns, which are really important when you're studying things like, the broader climatic zones or vegetation zones. Well, soil moisture obviously is important to those as well. Here, let's see how we can kind of compare one of these to another. In this particular case, you would read this as having the months of the year across the bottom. You've got obviously your temperature regime is shown here, as well as the precipitation is kind of in the blue there. As you have your increases in temperature, in our region, Atlanta, obviously this follows very much like we have in Nashville. Starts out cold, we have a distinctive summer peak, and then it goes back into the winter, right? Makes all perfect sense. But notice, and that's really reflected in all of these, right? Because we live in the temperate hemisphere. I mean, we're all going to experience a distinctive summer pattern. But where it really matters, and what I'm trying to show you here, is about moisture, right? And the interaction between temperature and moisture. So let's look here. In the case of Tennessee in the Mid-South, which is what this focus of this class is, we are fairly consistent in our moisture throughout the year, even when we see that summer spike in temperature, okay? That means that the amount of rainfall we get, and it is slightly elevated in the winter months, and I hate that. I don't mind telling you that. I mean, I get a case of the winter blues, November to February, it's like, oh, man, I need sunshine. A lot of people, their mood is affected by cloudy weather and too much rainfall. The older I get, the more I want to live in a sunny region to get away from that. And so you can see that reflected here. By the time we hit November, about Thanksgiving, we have a slightly elevated rainfall, and that continues usually into early April. And then we see that noticeable slide into summer and it gets hot. But even then, we have pop-up summer showers frequently. And yes, every once in a while, we'll get some severe droughts in the last few weeks. But let's take a look at that compared to, say, Nevada, for example, right here. Nevada's in the desert Southwest, and they typically have what's called a monsoonal rainfall scenario. So they get extreme temperatures, obviously, and they get generally low levels of rainfall, but then they tend to spike in that rainfall, particularly a little bit in that late spring, early summer period. And that's when a lot of their flowers bloom, okay? So anyways, we don't need to get too deep into this, but I just want to show that how this sort of generally might be anticipated. What this means, let's just summarize it. What does that mean generally for the soils of the Mid-South? There's two things I want you to get from this diagram right here. What's one of them? Soils of the Mid-South generally are what in relation to temperature?
Utic.
They are Utic. Good job, Laura, which means they are what? They're generally pretty warm. In this case, they're generally pretty moist. Actually, Laura, that's a moisture term, right?
Yes.
So they're generally pretty moist. They're not like the desert Southwest. So in relation to that sort of purplish background color, we have ample rainfall all year round, which means that our soils stay moist. But remember what Theo said about those mounds that formed in Arkansas, right? Why did those mounds form? Ian, do you remember? It's okay if you don't, yeah. Okay, so Chase? Dry periods, right. And remember, he showed some images of other places around the world where those mounds are actively forming. And they're in like semi-desert regions, very arid regions, right? And he said that the most recent example was that those mounds were how old? 600. 600 years old. That's just several human generations back, right? That's not that far back in time. He thought they were most researchers thought they were in the 7,000 to 9,000 year old range. 600 years was groundbreaking, because what that shows is places like South Arkansas went through some severe droughts, probably, which led to dust storms blowing up the equivalent of small dunes, right? Kind of like the Dust Bowl of the Great Depression days out in the Southern Great Plains. So while we are blessed now to have a relatively equitable rainfall, meaning equally dispersed throughout the year, we're not guaranteed that, particularly under various scenarios of climate change. One of the projections for this region, the Mid-South, is that we will get hotter, we will get more explosive and unpredictable rainfall events, and that those rainfall events may come less frequently, and hence we may have more drought and possibly more wildfires. So if those changes happen, our current climate regime could change hundreds of years from now or a few thousand years from now. One last example, take a look right here. This is from the Smoky Mountains region of North Carolina. Notice here that the temperatures are lower because it's higher elevation, it's cooler, right? And it also gets a lot more rainfall relative there. You have ample low temperatures combined with a lot of rainfall means those soils are pretty cool up in the mountains. Therefore, you can grow things like fir trees and spruce trees and support ultimately species like red squirrels or the Carolina red squirrel, which is endangered. All right, let's switch gears now. Let's go to topography and landform. Now, this is obviously not the Mid-South with this image right here. By the way, that is sort of akin to the Obed River Gorge example I was telling you earlier, where we did a project for the National Park Service. The key difference is, of course, this is somewhere out west. That's in Washington State, in a semi-desert region. Here, although we have similar landforms, we have trees everywhere, right? Because we have ample rainfall. But imagine being off in one of those canyons with a massive flood that's 40 feet high, tumbling boulders down the river. That's kind of what we're talking about. Here we could begin to see the dramatic impacts of topography, different types of landforms. We have a little area down here where we have some floodplain deposits, for example. We have toe slopes, we have cliff faces, we have a plateau. We have all kinds of other different sort of things. You have benches, for example. Who knows what this term is called, where you have all these piles of jumbles of rock at the base of a cliff line? Ken, what you got? Were you thinking of an alluvial fan?
Yeah.
It's not that, for one reason, primarily, and again, as a non-geologist, right, as a non-geomorphologist, you would expect an alluvial fan when you have a river entering, carrying those sediments off of the mountain. In this case, it's the collapse of rocks off that face. This is called there's several names for it. We're going to give you one called a talus slope, T-A-L-U-S, talus slope. And this is due to, collapses of rock fragments from up above through landslides and those kinds of things. Here's a pretty dramatic image from out west, probably California, showing the differences between different slopes. Aspect is very important. You get on a north-facing slope or a south-facing slope, combined with particular rock types and soil depths, it can create these repeated patterns on the landscape, which means that you get one ecosystem here on this southwest-facing slope. You get a completely different ecosystem on the north-facing slope, right? Different ecosystems or different communities, totally different assemblages of species, different abiotic processes, different levels of solar radiation, different moisture levels in the soil, different possibly bacterial and fungal populations. So all those things matter, and what's driving it here is topographic diversity and landform. Generally speaking, the more topographically heterogeneous the landscape is, the more broken and diverse, the greater the biodiversity. Chase? Now, this is a photo that from Theo, and here, this is Arkansas. One of the things you can see is the dramatic effect of aspect here. These are north-facing slopes on the right. These are south-facing slopes on the left. Just tell me some of the general differences you observe through looking at these two different landforms, the north slope versus the south slope. Actually, these are aspects. Which side? Left side, more water. Okay. I would say it's the opposite. What makes you think it has more water? A lot of the greenness, right? So yeah, that's a good observation though. Let's get back to that, which is a lot of, this is a winter photograph, obviously. Not much green here, right? What are all these types of trees? They're oaks, hickories, and they're all deciduous. Good point. On the other side, a heavy abundance of pine. Pine likes drought, likes dry soil, likes sandy soil, acidic soils. And from Theo's presentation, you might have noticed it also likes what? Fire. Okay. So a north-facing slope here. If you ever walked in the woods, like about right now, for example, or maybe a few days ago, after all the snow began to melt, you go into a wooded hollow or ravine, or you're driving down a road, you'll see that one of the reasons why around here they close school for days and days is because these protected slopes that are north facing, those roads have ice and snow for many more days as opposed to the south facing slopes, right? And so they're dangerous. Here, if you were to get, snowfall, this area is going to hold that snow longer because it's protected more from the rays of the sun as opposed to that south facing slope. So that aspect's really important. And it drives things like how much vegetation develops. Like, are these moist forests versus dry? Is it fire prone and hence grassy, right? The more fire you have, the more open the ecosystem is, the grassier it is. You need some fuel to carry that fire, right? Fire can't just burn across bare rock. And the more trees you have, the more leaf litter you might have, right? The more leaf litter, what might you expect with the soil?
Material.
Richer, more organic material, more carbon, more stuff living in it, more moisture, right? It probably has a temperature moderating effect. All right. And then deeper soils over here because of that. And then on this side over here, you might expect shallower soils, more fire, there's more erosion potential. That's not necessarily a bad thing, but what that means is you have more bedrock exposure, which provides more habitat for species that need hot, dry, open, sunny rocks. Like what? Give me some examples. Western diamondback rattlesnakes. This is one of the few places in Arkansas where you find them. Fence lizards, right? Collared lizards, Ozark collared lizards, etc. All kinds of snakes and reptiles could be here. Rare plants, many species that Theo was talking about earlier would be in these kinds of places. Now, what I want to next move into is a series of sort of hierarchical terms, right? These are kind of nested within one another. This is a classification. We are not going to get deep into this. I'm going to skim the surface and we're going to keep right on rolling. But people who work with landscapes sort of group things according to large classifications. So for example, water bodies, right? Put them all together. Wetlands all together, right? Places like glacial landscapes up in northern Canada. Aeolian, which means wind blown. So those features that Theo was pointing out, those mounds, those are Aeolian features. These are wind related landscapes. And just a couple more. Fluvial means related to streams. Lacustrine means related to lakes, like natural lakes. So I don't care that you memorize those. I don't even want you to memorize them. I just want you to know that these are called geomorphic environments. And within them, we're going to recognize three groups, two of which are really important: landscapes and landforms. And then we're going to briefly touch on something that Theo even talked about. He said the word microtopography. Remember that? Very small scale changes in elevation matter to those little bitty species, like the little people plant he's talked about, which is only a few centimeters tall. But we want to focus on these landscapes and landforms. And so give you an example of that. Within, let's say, a lake ecosystem, a lacustrine environment, you can have as a landscape, a lake plain, okay? As a landform, you can have a lake bed. Now, what I'm going to do for you is, and I already have given, I've got this for you here, is a variety of landform terms that you need to make sure you know, okay? And I suspect it's kind of like one time somebody says, do you know your birds? And I've never taken a bird class. I mean, from the sounds of it, I hadn't had soils, I hadn't had geology, I hadn't had birds. I don't even know if I should be teaching. And I said, well, you know, I've never had a bird class, but I've studied bird books occasionally. And I might surprise myself at how many birds I know. So one day I went and got the Peterson Field Guide and I popped it open and started counting. Like, yeah, blue jay, I got it. Sure, cardinal, yeah, bald eagle, obviously. Golden eagle, never seen one, but if I saw one in front of me, I'd recognize it. Count that. And by the time I got through and made my checklist, I knew like 78 bird species. I was like, yeah, I'm a pretty decent birder, probably better than your average. So I suspect most of you know many of these terms, because what you're going to notice is I've got, I don't know, probably 50 of these dots placed on here, and you need to know them. But guess what? They include things like plateau, right? Stream, river, basin, valley, stuff that we've all been kind of learning through our life, through general wisdom. So some of these are some of the landscapes here that I want to kind of generally introduce. Let's look at the concept of landscape versus landform one time. This is a canyon landscape, right? The landscape is a broad category that includes all these different landforms, okay? Think about some other ones. A mountain landscape includes all kinds of mountain landforms. A plateau landscape includes plateau landforms. A valley landscape includes valley landforms. And finally, I'll give you one more. A hilly landscape includes hill landforms, right? Pretty simple, but these are important. And I'm leading into this because what I want to do is I'm going to show you a couple of really important references that many of your, many folks who are out there working professionally as biologists need to know these terms, or using these terms as part of their professional day-to-day job. So landscapes versus landforms. Let's dig into some of those landforms a little bit more. Now what I want you to think about is the term landform versus these micro features, okay? Landform in this case would be like here, you've got this sort of hill, right? You've got the crest of the hill, you've got the hill slope, you've got an alluvial plain out there. Those are all specific landforms that we think about. We can map those, right? We can define and describe those. And they're sufficiently of a size that you can map them. However, when you're at a very small level, like these little pimple mounds here, those are obviously way too small on the landscape for us to be concerned with. Are they important for species? Absolutely. Because in here, in these little pockets, are going to be species of plants or salamanders or certain types of insects that, guess what, are not right there. So yes, you need to be aware of microtopographic features. But for right now, I want the focus, your focus here to be on landforms, okay? A slightly bigger level. Here's a few of these. I'm just going to call out a few of them. You've got the PowerPoint, and you will have the PowerPoint. And, you know, things like a bar, like a sandbar. You know, a dome. Laura mentioned, what is a dome? Flatwoods, a fen, cuesta. We mentioned that word the other day. A bog, block field, I mentioned today. A gap, you know, a plain, a marsh, an interfluve, a point bar, a sinkhole, a slough, cliff, right? These are just a few examples. A stream terrace, a swale, a swamp, a wind gap, or a valley. How many of those terms were familiar to you already, generally speaking? Like what percentage would you say you were just generally kind of familiar with? 30 to 40%? Something like that, right? There's some new ones for sure you're going to need to know and think about. But generally speaking, most of it's going to be pretty straightforward. Let's look at this now at a finer level, specific to the hill landscape. Let's look at the landforms that make up the hill landscape. So for example, here in this diagram, we call these block diagrams. You can see here is sort of a typical sort of hilly region. These are some really important terms that are used a lot in describing natural landscapes. The top area between sort of two stream valleys is known as an interfluve. You've got a side slope and a nose slope, the base slope, for example, and a head slope. And then, of course, you've got, once you get off of the hills, you're in a different landscape. You're in a valley landscape at that point, which has its own landform terms. So here's just a few. There's some definitions. Again, I'm not going to hammer you on these. I just want you to generally work your way through and be familiar, because here's what I'm going to do. I'm going to sprinkle them through all of my discussions through the class, right? You're going to hear me start talking about a back slope and an interfluve and an alluvial plain and a cliff face. And I promise you, if you just pay attention, even if you don't study your heart out, if you just hear me and hear my stories and come with me, I promise you, you will pick a lot of this up just through that osmosis process right there. It could get real complex real fast. I promise you, I don't even want you giving this much thought, but just look at the complexity of things like how those slopes are, right? Geomorphologists, and there's whole classes on this topic, they study this stuff and they really think a lot about it. There's three basic concepts here I want to just kind of show you, and that is on a slope, there's two or three things that really matter. Is that slope sort of straight? Is it concave, right? Like here. Is it convex? How might those matter in the scheme of moisture retention? Okay. If it's a convex slope, chances are it's going to be very dry and drought prone and rocky or gravelly. If it's concave, it's going to hold more soil and more moisture. All those things are going to depend. Okay. Now, if you look at slopes sort of from a side view, then we've got some additional terms here. At the very top, you've got the summit. You've got sort of this upper edge we call the shoulder. This sort of drop off called the back slope. And then when it gets to the bottom, you've got the foot slope, followed by what's called the toe slope at the very bottom. Every single one of them, if you were to map soil types on them, there are probably going to be 1, 2, 3, 4, 5 distinct different soil types right through on that landscape. These are generally, the soils are so specific, they're different for each of those landform positions. Okay. Now, here's what obviously a more kind of a complicated where you have terraces. We don't need to get into all that. So what are the key aspects so far? What are the different terms called of these landforms? Just have a working definition of those. Understand that aspect is important. That makes sense. Things like the degree of slope or the grade is very important. That's going to matter. And what's the elevation? Are you up in the mountains or are you down low? These all are going to obviously matter as well. Okay. So with regard to sort of the degree of slope, let's break this down into very simple levels. Okay. Number one, there's about 6 different classes that you could recognize. Okay. Imagine it's very flat as this table, right? That, my friends, is nearly level, and it's got a 0% to maybe 3% range. So about like this, up to about like this, right? Okay. And then it gets steep, gently sloping, goes from 1 to 8 degrees. Okay. And so strongly sloping, moderately steep, steep and very steep. Why do we have these classifications? It's for the people in geomorphology to accurately describe landscapes. And a lot of this is captured in things like GIS models. We can ask very complicated queries because we have mapped most many areas of the American landscape, we can look at things and ask complicated questions about the evolution of landscapes and how ecosystems are tied to landscape properties, like things like slope. So if you need these data sets, they generally exist out there, right? There's a lot of data available to ecologists and biologists for study. Why would you need that? Many people in biology are modeling species distribution, for example, right? Well, you can't model species distribution and really know what the hell you're doing unless you have a good concept of how those data matter with respect to like the abiotic or non-living properties. So here's those percentages that I've just kind of written. And then this graphically shows what they look like, okay? So a 100% slope or 45 degrees angle, and then you can see those various gradations down. All I want you to do is spend some time looking at the red lines, okay, and correlating those with these percentage breakdowns over here, and just generally what kind of terms we use. Again, I don't want you memorizing a thing at this point, right? I want you conceptualizing, and I want you, more importantly than anything, it's like my daughter says, Daddy, I don't need to memorize it. Why not? I got Google, right? I don't want to, fish for you, right? Or whatever. I don't know the analogy. I just want you to know how to go to find this information so that when you go get a job with the National Park Service or the U.S. Department of Agriculture or a nonprofit, and I assure you, when you get out of the school and you got a degree in biology, sometimes you end up doing stuff that doesn't allow you to use your degree. You got to be a jack of all trades. You got to know some soils. If you got your degree in botany, so what? You may be capturing animals, right? You may be cleaning bathroom stalls. The point is, knowing where to go to get this information is often sometimes just the hardest first step. As I said, this relates to soils. And so you would expect then soil 1, soil 2, soil 3, soil 4 to be in these different places on these slopes. And we're going to get especially more into that in our next class. All right, I'm going to speed up here a little bit. And these now are some of the landforms that we would associate with sort of like stream terraces. So two terms here in particular. You've got on these terraces adjacent to these rivers, you've got these sort of flat terraces here. And then you've got sort of the slopes that we call the riser. So the tread is the flat and the riser is that slope, okay? The tread and the riser. On mountain systems, again, I'm not going to expect you to go through all these, but you've got different kinds and parts to that mountain system that are important to just be aware of. Same thing for plains. So we've gone through now and give you some examples from hills and mountains and plains, and you can see we've got rise and tuff and dips, and you've got sinkhole ponds and those kind of things. We're going to get into a lot of this slowly over the course of the class. I'm really wanting to just introduce the concept of landforms today as a concept. All right, and then lastly here is micro features. These are some more of those pimple mounds that Theo showed that are out in the middle of these prairies. Those are really too small for us to concern ourselves with. Oh, ordinarily though, what kind of landscape is this? This is a plain landscape, right? And if you look back and say use some of these kinds of terms, this sort of flat portion of the plain will be called the tuff. Right? If you have a little dip off over there somewhere or a rise, those would be additional terms that we might employ. And then here's some of those pimple mounds as Theo showed you when we look at those on a map. We're going to now move into relating the sort of general content that applies to various parts of the country, specifically to what's happened around here, okay? And this is the lecture is going to carry into next Tuesday, and that's okay. We're going to next introduce what are called block diagrams, all right? Get a sip of water here. All right. So block diagrams are pretty cool. These are three-dimensional representations of a given area. What I love about them, by the way, this shows the area north of Clarksville. This was made up in Todd County, Kentucky. And it shows the underlying limestone formation. It's clearly labeled. It's got a mantle of another type of unconsolidated sediment called loess. Remember, we introduced that, I think on day one. And then, so it's showing you what's happening underground. It's even got cave systems and showing how those are connected here to these sinkholes, for example, right? If you live in Clarksville, you know sinkholes are kind of a part of our community and a part of our life. We wouldn't have Dunbar Cave State Park without these sinkholes, right? What do we call this open plain then that is underlain by cavernous limestone? What's that type of plain called? What kind of landscape do we call that that has an abundance of caves? It's a karst, or how did you pronounce it? With a Y on the end? Okay. A lot of times in ecology, we sort of drop the Y and just say karst, a karst landscape. From the geosciences, they say karsty, which is cool. Okay. So this is a karst plain. In fact, and we get into a couple lectures, one of the things we're going to do is review the different ecoregions that have been named around here. And we are technically in northern Montgomery County as part of what's called the Western Pennyroyal Karst Plain ecoregion. Right? So that's a region that is characterized by being an open plain, generally undulating sort of topography, not a lot of hills and not a lot of mountains, okay? As opposed to this landscape, which comes from just southeast of Clarksville. This is down near Ashland City, between here and Nashville. Notice how hilly and dissected, and it's got the Cumberland River Valley going through it. This is part of another ecoregion, which is here actually on campus. We're kind of on the border. If you go from here south toward the river, toward Dixon, you're in the Western Highland Range. If you cross the Red River, like you go up to where Sonic is, and you know, go toward Montgomery, Dunbar Cave State Park, or out through the mall, you're on the Western Pennyroyal Karst ecoregion. So south of campus, you're in the Western Highland Rim ecoregion. Now, we're going to learn all these. That's a big part of, for the early part of class, is learning these ecoregions, and importantly, learning how the ecoregions are connected to both the underlying geology and what? Soils, right? That's what these other, the other thing these block diagrams give you is they give you the soil names, which in this case are called soil series, the Kreider series, the Pembroke series, named for Pembroke, Kentucky, right up in Todd County. The Vertrees series, the Linside series, and so forth. All these have these different series names, and these are largely sort of locally derived names. Okay? So I like these. They show different features of the landforms, the soil types, the underlying geology, and they sometimes even show features like certain rivers and whatnot. But they're really convenient ways to kind of organize the landscape into a three-dimensional sort of view. Now, I have included here some links that are pretty cool, and I'm going to let you guys sort of explore that on your own. But basically, this will take you to a USDA website that allows you to look at an interactive map, and there are little icons on the map, thousands of them across the country, of block diagrams. So if you want to look at representative diagrams from your hometown, or New York State, or Wyoming, or Utah, there are block diagrams for all these places, and those are pretty helpful. Okay, and just sort of finishing up here in our last sort of few minutes here, I now want to introduce this concept of these soil, the soil series that we just talked about, those Kreider soils and Pembroke soils, the ones that are named there. These have all been mapped, and it's actually quite remarkable if you think about it, how extensive the landscape is well known and understood from a soils perspective. We don't even begin to have this level of understanding for other things, right? we have, sure, we've got topographic maps, but even geologic maps are very poor relative to soils. There are whole sections of the country that the geologic maps are still very coarse, very imprecise, almost unhelpful or inaccurate at the local level. Soils, on the other hand, are really accurate. We have piss poor maps when it comes to like, where is fire naturally on the landscape? Where do certain species occur on the landscape? We are still in the dark ages in some of that, but not with soils. So the good news is soils serve as a pretty good proxy for understanding geology. Why? Because they're derived from the underlying rocks, and they're a great predictor of what else. Soil types tell you a lot about a lot of things, especially what type of ecosystems to expect, okay? Certain types of soils are naturally associated with forests. Other soils are naturally associated with grasslands. Some naturally associated with swamps. And for that reason, and they're naturally associated with these different landforms. So soils have high predictive value. So if you're doing modeling for a given species of salamander, you probably want to know that you can access soils data and incorporate those into your distribution models. If you're modeling trees, you want to know that you can access soils data. And believe me, all this is available in GIS, which is really a strong complement to biology these days. Okay, the last thing I want to end with is if you were to go and look up each one of these types of soil, let's say like, the lindside soil, for example, right here, right? That one appears to be associated with a slight depression. Looks like they've kind of drawn a little stream through there. But notice it's not a river that actually connects to anything. It's sort of just a little ephemeral stream, or maybe one that's not connected to a broader water body. You might expect those to be wet based on that low position, okay? Are there any other expectations you would have of the lindside soil from looking at it? Anything come to mind? Any projections or predictions you might make? Like, would you predict anything about what kind of ecosystem should be there?
Looks like it has
keep in mind
distinct
this-
margin.
Say again, go ahead.
Who, me?
Yeah,
It looks like it has a really well-defined and distinct margin. Like, would that be some geographical feature that limits it like that?
yeah, it could be the edge of a sinkhole, right? Maybe it's depressed because there's a collapse underneath it where that lindside soil is occurring over what's called what's the term for that? Sinking valley. There's a karst valley. That's what I'm thinking of. That's one of the landforms. So what I'm also getting at is would you project or predict that the lindside soil, because this was mapped in like the 1960s, right? 150 years after white settlers came into this area and started cultivating stuff and plowing everything and cutting all the forests down, right? That's a lot of what we sort of imagine. But what was it really? Was the lindside soil naturally a swamp? Was it all forest? Was it a prairie? What do you think? And what other clues to the landscape would help you develop your prediction? Anybody? This will be our last talking point, and we're going to adjourn. Actually, we're at time right now. Any thoughts before I wrap it up in sort of one statement? All right, I'm gonna leave you with this. I don't want to tell you the answer, but I want to tell you about fire. Okay, imagine that lightning strikes somewhere over here. Okay, and then a fire breaks out, and that fire begins to burn. In this landscape, do you see any large rivers or creeks? Okay. Do you see any wetland soils that are obviously so wet that it might stop fire? We don't know that, right? We'd have to investigate what the criter soil is Is that a marsh, or is it just a flat grassland, or is it just a flat landscape? The point being is that fire moves across a flat landscape real easy. Okay? Does it move up and down hills real easily? It can go up hills very easily. It does not like to go down. So if you have a highly dissected broken region, you expect then that those broken areas, those valleys, tend to be forest. If you have wide open plains, these plains of Africa, right? The Great Plains of North America. These flat plains up in southern Kentucky, up around just over the state line, you might expect those to be able to carry fire. You might also expect those to be able to be an open ecosystem. Okay. So just things like the presence and absence of creeks and streams are fire breaks. If you don't have them, then fire could be expected to carry. I'm going to reserve anything else because I don't really know yet whether this was all forested historically or all grassland historically. We're going to continue to explore that in our next class. When we meet again, what I'm going to begin to do is work with you to understand how to read each one of these soils and infer the basic properties of it. Is it acidic? Is it made of clay? Would you expect salamanders and burrowing crayfish to be there? Would you expect bison to graze there? I want to give you the attributes that are going to be useful to you in your careers. All right, that's it. Thank you guys for a couple extra minutes here. Can you see the relation to landform, by the way, to soils? It's really important. And I know it was a long-winded discussion, but I wanted to make that point clearly because you're going to need it once we start going here. All right. Everybody online, thank you for your time. I appreciate it, guys.
Thank you.
Thank you.
Thank you.
Thank you. Soils. Okay. What else? We got the geology and landscapes. Those three components, right? Now, what is it that we're trying? Why are we connecting those three things here and now for this class? Why do we care about geology first, soils and landforms? Why do we care about those? Chase? They affect everything. They kind of set the stage, right? If you think about a play that's being acted out, and this is the stage of life. And so we want to make sure that we pay close and careful attention to setting that stage properly. And I think as we discussed is, sure, you could get some of these classes in your experience as an undergraduate or graduate student, but some of you might not, right? You might get completely out of your program and out of school without having had exposure to some of these key concepts. So for the purposes of this class, just to bring it back clearly into focus, if our focus is to teach you about the general natural history of the region, of its ecosystems and landscapes, then obviously these are the key building blocks that we need to begin with. Now, the other day, I felt like sort of toward the end of this particular lecture, which was the midpoint of this PowerPoint, and we're going to finish this PowerPoint today, hopefully in the first hour. I felt as if I was getting a little bit dry and long-winded on it, which I tend to do. In fact, I had my graduate student last time I taught this class, he had a sign that he made. So whenever I got long-winded, he just hold the sign up. Basically like, shut it down, buddy. We got it. Point taken. You know, I don't think we want to get to that point again. You know, I'm not asking you to make a sign, but you know, you can like do this right here, or, you know, give me some kind of a mark, you know, a twitch. Yeah. You know, just make something to say, hey, let's move this along. We got it. But all right, we're going to start back there with landforms. And I also realized one more key point before we jump in, and that is that, you know, I covered a bit of material where I would say things to you like, I'm not going to hold you responsible for that. I'm not going to make you memorize that. You heard me say that a few times. And I think that's because in this effort, I'm putting into this PowerPoint, for example, here, is a link to block diagrams. It's a whole website, and you could explore this to your heart's content if you wanted to learn more about block diagrams and really dig into that. And sure, I could have you memorize a whole bunch of stuff related to landform types, but I would rather weave this all into this giant story that we're telling through this whole class. So that, and sometimes that goes against the grain of the experience of being a student in a class. And I have to remember that the way I'm teaching you and the way you guys learn best might not always be in sync, okay? Because I have my way of teaching this class and the ways that I kind of want to, the way I like to teach is the Socratic method. I like to talk and I like for you to just soak it in, you know? But more importantly, I want you to hear this class and experience this class as a long-winded story, hopefully one that's somewhat enjoyable to listen to. And I realize at times it's dry. You know, that's why I have you stand up and we stretch and, you know, roll our arms around and all that kind of stuff. And by all means, if you need to get up, walk around, you can do that. You won't break my stride. I have been known to lecture for 11 hours in one day. So I'm cool. I can handle it. But I want to tell you this as a story, and I want to weave into this story bits and pieces all along the way so that, you know, unlike in some classes where, sure, you need to know that material then, you need to force feed it into your brain then at that moment and before you can go on. I do want you to do some of that along the way. It'd be handy, but more importantly, I want you to know where to go to find these resources because you will need them again as a professional, right? And I want you to be able to know sort of how and where they fit into the story. And if you listen to the overall story, that's what I want you to focus on. Because any of us could get lost in the minutia of all the material I'm about to throw at you. So I just want to reiterate that. Okay, so block diagrams were just the way we were sort of conveniently making the link between soil types and geology and landforms. So take this, for example, right here. These are two block diagrams that come from an area within about 30 miles of Clarksville. On the left is a block diagram that is from the area right out around Ashland City, so about 25 miles to our southeast of here. And then if you look at this one, this is from up in Todd County, Kentucky, roughly 20 miles north of Clarksville. On the left is what you see is kind of a river valley that's bordered by hills on one side. And so you've got a mixture of floodplain environments, floodplain landscapes, and hilly landscapes. And then, of course, within that, you've got floodplain landforms and hilly landforms. And I realize I don't expect you right now to know all that stuff that I went through last lecture, like what's a back slope and a shoulder slope and a toe slope and a foot slope and a summit. I'm going to weave this into this long-winded story throughout the class. Okay. And then likewise for the floodplain landscape, I don't expect you now to have instantly through osmosis understood what an alluvial plain is and what is a point bar and a bar and swale landscape, or even a gravel bar or a meander scar or an oxbow lake. Those all will come again, time and time, we'll weave them into our story. Now for this landscape on the right, this is a little bit of, slightly dramatized. Obviously, we're looking at a particular square patch of land. Let's break it down into all of its components and see what we're looking at, shall we? So right now in this block diagram, three-dimensional view, we can go down. We are obviously seeing the underground geology here, which is represented by just a couple of quick layers. I frankly think they did this one kind of hastily. They could have drawn some more rocks down here, right? They could have done that. It gave us a little bit more on this side over here. But in essence, all of this would be limestone, and in places, some of that limestone would be eaten away as caves or caverns. And then what's on top of that limestone? What do you see? Yeah, it's loess, and that's a particular deposit. Remind me where loess comes from. Anybody? Where do we get loess? Wind-blown soil, yeah. Specifically, one of the ways that we get loess around here is it's kind of like a blanket of soil that's been blown by the wind and redeposited. And a lot of that, you say, well, man, how does that happen? Well, you can imagine sand dunes, right? Getting shifted by the wind. That makes sense in deserts. In this case, this is where you had glaciers that were moving and grinding. Now, just imagine for a second that you had a couple of rocks. Something like this, these two rocks. And this rock is the surface of the earth, right? This rock is a giant glacier of ice. And imagine then that with all the weight that this is, and this is part of the land surface, that this glacier is depressing down with, just an untold amount of weight from that ice. Not only is it forcing itself down, but then it's moving, right? It's grinding. And as it does, did you see all that? As it does, it's grinding all those sediments with it. And that sediment, because it's grinding so slowly and so forcefully, has the texture of flour, just like you would cook with baking flour. And that flour then, which is basically rock flour, is one way we could put it, is just ground up, pulverized rock. This was happening sort of as the glaciers were grinding and growing. And that rock flour got trapped underneath thousands of feet of ice as the glaciers were advancing down out of Canada, across Illinois, into Missouri, Indiana, during the Ice Age. And this also happened out west in the Rocky Mountains and parts of the Pacific Northwest. You had these glaciers growing down. Same thing was happening in Europe and in Asia, coming down into parts of Mongolia and Siberia and much of modern day Europe, parts of Scotland and northern England were all covered in glaciers. So then what happened when it warmed up? The glaciers melted and began to retreat backwards, right? So imagine these glaciers having come south as far as Columbus, Ohio, Indianapolis, Indiana, almost to the Ohio River at the height of glaciation. And then they begin to melt and they retract, melting backwards, pulling backwards to the north, back into Canada, back toward Greenland. And as they do, they leave behind a wasteland that has been buried under ice for tens of thousands of years, that is basically completely open, denuded landscape, no vegetation, no nothing except pieces of rocks and boulders and rock flour. Now what happens is these winds blow across the glacial front. Okay, these winds, I think they're called adiabatic winds. Anybody know that? That's what they are, right? Yeah, adiabatic winds. These winds that blow along the front of the glacier. And what they do then is they begin to pick these piles of dirt up like a dust storm, and they blow them, and you can imagine dunes beginning to form, but it's not sand. It's even finer than sand. It's rock flour. And then this begins to settle and accumulate in deep piles, particularly where you have things like a river. It might blow across the river and land on the other side where there's a natural hill. Sort of like a snowdrift, right? We get some deep snows in the winter occasionally here. Or if you live out in the Midwest, you'll get deep snowdrifts up against fences and up against trees and against slopes. And so the snow normally might be 6 inches. If you got a lot of wind, you can have a snowdrift that's 3 feet deep. That's what's happening. When you get something those piles of windblown lusk can land against, they pile up and they pile up and they pile up and they create gigantic hills, 90 feet deep, 100 feet deep, 50 feet deep. Now, the farther and farther they get out from the glacial front, then they begin to just form a thin veneer, like a blanket. So like here in Clarksville, that lusk layer, which you can see out off of Trenton Road and off of Dover Highway, if you find a place where the highway is cut through the bank, you can see sort of that brownish orange soil. And then right on the top of that, if you know where to look, is a very thin layer of extremely fine sediment, and that's all windblown lusk. That came because it was blown down during the ice ages. And this is about the southeasternmost end of it. So it covered a lot of Middle Tennessee and central Kentucky. But if you go west and northwest toward Memphis toward Iowa, you can actually see extremely deep loess deposits. So anyways, that's what we're looking at here is this thin mantle of loess. I want you to understand where that comes from. That's a real critical part to our natural history of this region. Now we've got mostly an open plain landscape here in this case. And this plain landscape has rises and swales and dips. And it's even got in places these sort of low hills like you see here. So it's not a perfectly flat plain. Anybody who's driven up through Hopkinsville or Trenton, Kentucky, or in the countryside, just in the north side of Montgomery County, you know how kind of rolling that plain is. Now what we want to do is we want to connect one of these landscape types, or one landform, specifically this one, these flats, that are associated. Why do we have these sort of flats in the first place, or these kind of sunken depressions? What's the cause for that ultimately? Yeah, and we know that in this case because of why? At least in this block diagram, immediately under it, there's a sinkhole, right? There's a cave. And so what's happening then is this cave is, it undergoes periodic collapses, and all those sediments above it pour into the mouth of that cave system. But sometimes the roof of that cave collapses entirely. Think about our football field here at Austin Peay campus. Was anybody here, or do you remember like 5 years ago when like the end zone out to the 30-yard line completely just sunk in, boom, with a giant sinkhole? Yeah, Google it. It's crazy. They ain't spent months on a brand new football field repairing this massive sinkhole because we're on a karst plain right here. Just out here on the edge of campus, or on the edge of the parking lot going toward the football stadium, there's sort of a bowl-like depression. We call that the bowl. And lots of our basic ecology and plant ecology classes sometimes go over there and do measuring trees and stuff. Well, that's also a sinkhole right there right there on campus. So imagine then through the course of thousands of years or tens of thousands of years, if you had multiple collapses in and around this all over a cave system, that it would go from being something like this to where those sinkholes would coalesce, forming eventually a collapsed landscape that has that becomes sort of a sunken plain. That's what we're looking at, right? Okay. Now those soils in that collapsed sinkhole are unique from the soils that are up on the hill slope above it. Why? What would make those soils potentially different in that, say, landscape compared to, say, over here? What might you expect the general differences of the soil properties to be? Anybody? Juliet, what do you think? They may be thin up on the hill, and they may be deep in the depression. Excellent. Good point. Anybody else? That's one I was thinking about. Let's think about three properties. So soil depth could differ. What else? Sarah, what do you think? Excellent. Yeah, it's probably going to be saturated because it's catching all that runoff, right? And it's flat. The flatter the landscape, the more likely it is to be saturated. And that's going to be enhanced if there's something underneath it that prevents soil water drainage. So if you have a real dense clay layer, or if you have a solid layer of bedrock, then that water can't filter out easily and it just sort of settles, right? So it can make it wet. All right, what's one more property? Okay, particle size could be different, right? You might expect one to have sand grains or sandy soil, and the other one might have like a clay loam. Clay is small, very small particles. That's absolutely possible. The last one I'll just say is nutrients, the way nutrients sort of cycle out. Oftentimes, higher sediments like the one on the top of the hill, up in the summit of the hill, or the shoulder slope, the upper slope, those might tend to be more strongly leached of their nutrients. Therefore, they tend to be a little bit more acid sometimes, those soils, because their bases, like calcium and magnesium, have been leached away. And those bases then are carried into lower elevations where they may accumulate somewhere else in another type of area. So you could have soil leaching of nutrients up here, and through runoff, those nutrients could be carried into a lower area like this basin here. All right. With that, let's go on to the next slide here. Okay, now these soils frequently then are being mapped nationwide. So if you're in Colorado or Maine or Tennessee, a very common source of information that you might need as a biologist or an ecologist is you may need soil maps. And so it's helpful to understand kind of how to read these maps and how to make use of that information. The soil diagrams, the three-dimensional block diagrams, is just one sort of helpful way to kind of know. And as I mentioned with that previous link, if you click that, it'll take you into an interactive map, and you can actually look at diagrams that are sort of near you. And there's some gaps, but generally speaking, it's pretty helpful. Now, when you look at a soil map, a soil mapping unit, for example, we're going to focus on the Crowder soil here, which is this one in the basin right there. If you take a look, excuse me, we're going to focus on, I've got the Lindside soil right there as my example, the Lindside soil. If you were to go and look up the data that supports that soil, there's all kinds of information associated with that. And it can be quite a lot. You know, you've got things like, what's the elevation range for that particular soil type? What are some of the climate data? Like, what's the rainfall at that particular area? You get on down in here and there's like, what landform is it associated with? In this case, closed depressions and floodplains. What's the parent material? Ultimately, like what underlies that soil that is partially derived from? Mixed fine silty alluvium. So what that tells you is that ultimately these soils originated by alluvial deposits, which means that there was one time a stream or a river that was probably depositing sediments across this flat plain. Okay. Then it kind of goes through some profile information. So what does the top layer of soil look like? The A horizon, the B horizon. We're going to get all that in a little bit. More properties here, like what's the slope? How deep is it to a restrictive layer like bedrock? Things like the frequency of flooding and ponding. Is it a wetland soil? That's very important for people working in ecology. You want to know if you're dealing with wetlands a lot of times. And so there's all kinds of very useful information that you can find here, and it can frankly be overwhelming. And what I want to try to do is kind of break through that and show you how to kind of work through the most important parts. Now, in modern mapping of soils, of course, everything now is based on GIS, and everything is usually available via shapefiles. But essentially what we're doing here is we're taking the finest unit of a soil, which is called a pedon, P-E-D-O-N. A pedon is sort of this conceptual hexagonal, almost imagine if you stuck a pipe in the ground and pulled it out and it had a soil core, right? That's one pedon. And you can, don't worry about all the name of the soil here and the profile, but basically what you can see is that this particular pedon, and here's all the layers of that, the A layer and the various the B horizons as they're called, comes from this point. It's almost like a honeycomb. And so you drill down and you get that one out. That one by itself doesn't tell you really anything, okay? You really cannot map an area based on a single sample. What you need is a collection of pedons, what's known as a polypedon. And so it's by understanding these polypedons where we kind of understand, yeah, all these soils are related to one another, sort of genetically related. Not in the DNA sense, but, you know, in the soil kind of related sense. And so if you look at this, for example, underneath the soil layer, again, don't get lost in the specific names of this, you know, these can be kind of technical. But what I want you to focus on is just take a look at underneath this particular soil. Basically, all this is saying is that you have a very clay-based soil here across the entire area. But this particular area here has a hard calcium layer under it, right? But not here. It's like a window through the soil where this hard calcium layer is missing. So what we're just basically saying is if you were to sample that with your core, if you were to sample over here in a couple of pedons, you'd be sampling in this area that does not have this real hard layer underneath it. If you were to sample over here though, right, or over here, it would have that layer underneath. And that's reflected, as you can see right there, right? Does not have it versus it has it. So soil scientists, then, they go to work and they map these things. They go out in the fields and across the hills and they're using soil cores and augers and some cases like backhoes to really get a deep profile to look at the soil. And essentially then what they're doing is they're mapping this ultimately. Here is one soil type, and then this would all be mapped as another soil type. And then all that gets classified sort of at this pixelated scale and put into a giant GIS, Geographic Information Systems. And then we can see each one of these gets a name, right? The DeKalb soil, the Elkin soil, the Gilpin soil. This is for a site in West Virginia. And this becomes exceedingly useful because these soils have properties that relate to, is it a wetland soil? Is it a soil that occurs exclusively with grasslands? Is it a forest type soil or a bog soil? And so by mapping the soils, which is an available data set we can all use, think about that. If we're working for the National Park Service or the state parks, we can pull that in for our particular park usually. And then we can do all kinds of conservation planning, biodiversity planning, using that soils layer as a critical piece of knowledge. Did you have a question? Huh?
You answered my question.
I did, I got you. Okay. So soil mapping is extremely useful. There's a lot of these maps and just be aware of those. Now, again, we've already defined polypedon and pedon. We don't need to get too deep into those. Now, when I started out in natural history in the 90s, one of my mentors said, well, Dwayne, if you're going to get into knowing about plants, then here's some good references for you to know. He said, number one, you need to know about soils. I said, well, why do I need to know about soils if I'm interested in identifying trees and wildflowers and all that stuff? He said, just trust me, you need to know this stuff. So he gave me a copy of what's called the Soil Survey of, in this case, was Montgomery County. And I opened it up and, it looks very similar to this. It's got a front cover and it's about, I don't know, 100 pages or so. And in it was a lot of information very new to me. One of which was a description of what they call their soil associations. And this was totally new. And I looked at one, for example, here's the Pembroke-Baxter-Crider Association, or the Dixon-Sango-Guthrie Association. When I say that to you, Dixon-Sango-Guthrie, tell me what comes to mind. You live where? You live in Sango. So Sango it's a place, okay? I was in Guthrie yesterday. Guthrie's a town on the Kentucky state line. And today I actually live in Dixon County, just north of the city of Dixon. So all these are places, right? Why does that matter? It's because these soils are given type locations, very much how if we discover a new species of animal or plant, when we describe it, we ascribe it to a type, right? There's a type specimen that's fixed to a specific location. In this case, these soils, the Dixon soil, was typified because it was described from Dixon, Tennessee. The Guthrie soil was typified because it was originally described from Guthrie, Kentucky. And then when they go to mapping these things, they say, hey, this looks like that soil we found in Guthrie. We're going to call it the Guthrie soil, right? They classify it. Very much how we classify plants and animals, except we're classifying non-living material, in this case, soil. Okay, so then what we can do is we can put these soils into related relationships called associations, which seems to indicate that they're similar for some reason. Maybe these are all, in fact, there's a nice little description right here. The Dixon-Sango-Guthrie Association consists of these three soil types, and that's because they all are nearly level, silty soils that have a fragipan, which is a dense clay layer underneath, and they're all moderately well drained to poorly drained. That's what unites them all. You know, sometimes in evolution class, or we're talking about biological evolution, we think about traits that unite a particular group of organisms. You know, primates are united by, you know, specifically apes and chimpanzees and humans are united by multiple characteristics, right? Opposable thumbs and bipedalism, and that's not a great one because it's humans, but what's that? Shoulder architecture, right? What's some more? Relatively flat faces. You know, there's a whole bunch of things. And what we call those shared characteristics, y'all know the term for that in evolution? They're all homologous, and specifically we call those shared because they've been passed down from a common ancestor. There's a term for that, shared derived characters. It's called synapomorphies. Do y'all remember that term? Okay. In this essence, basically, what we're talking about with these soils is that they're similar because they've gone through similar experiences. They are derived from similar kinds of bedrock. They're derived from similar kinds of parent material. They have similar drainage patterns. And does that mean ancestry in the case of like DNA? No, it's not the same. But hopefully you get the analogy that I'm trying to draw. Okay. So soil associations are really helpful. They provide these long descriptions that are important ultimately to understanding the landscape. And what I want to do now is particularly point out the Pembroke-Baxter-Kreider Association. Let's dig into that. What we want to do is break it down to its component parts. And we're going to specifically dig in to see each of these associations is made up of what's called a soil series. So in this case, the Kreider is a series. The Guthrie soil is a series. Now, if we take a look at the Kreider series here, we can relate that back to our block diagram, and you'll see that here's the Kreider soil right there, okay? That's the one we were talking about earlier, that particular landform. And so with that, we want to start looking at this in a little bit more of a magnified view. We want to understand some of the characteristics that these soil series are given in the soil survey, in this document. So number one, we can take that block diagram, and in the modern form, block diagrams are not super helpful in the landscape, but we want to look at particularly are these very detailed soil maps. So here's a map from somewhere up in Kentucky, and we can actually see that there's the Kreider soil that is mapped out as part of that polygon. And it's given a code, CRB, right? There it is. And so this, this particular soil goes around and down and around. So imagine, if you're asked to do a report for a private landowner or a state park, and you have to describe the soils, this could be a way, you put this into GIS especially, you could estimate what percentage of that park is made up of the Kreider soil. And then I'm going to teach you in a minute how to pull out the necessary ecological materials that you need that are important to the ecology of that, okay? Now notice though that there isn't just one kind of Kreider soil. There are two. And within a series, you can have one type or you can have multiple types. You could have several. But in this case, we have just two to think about. One of them is called Kreider silt loam. That tells you a little bit about its texture. Notice it's on 2 to 5% slope. So that's like, you know, really, really gentle slopes, okay? The 2 to 5 would be, that's level. So 2 to 5% slopes would be something like that right there. Still out on the open plain, but with a little bit of a decline. And compare that then to the other type of soil here. And you can see that with that one, it's mapped in a different location. And what's the key difference here? Very simply, how would you describe those as being different? Yeah, right. So these are steeper slopes, right? Instead of 2 to 5, we might be looking at slopes that are a little bit more like that. And they've got the addition in there to say they're eroded. And that means that these have been subjected to soil erosion, probably because of history of farming, maybe overgrazing. All right, so that's the sort of first level of information. We're going to dig deeper there. If you keep reading about in the soil survey, typically they all have this table in them as well that provides a good summary of basic characteristics of those particular soils. So let's go look at the Kreider silt loam right there. And here's a few of the things that we can gather from this. So number one, text is real small. This tells us the parent material, so what it's derived from. So we've got that here, loess over limestone residuum, okay? These other kinds of soils, like the Guthrie, is derived from alluvium, so river deposits. These types of soils, the Baxter, are derived from Churty limestone. So again, you see the direct connectivity back to geology. That's a real key factor. Next, we're going to do is take a look at this factor. This happens to be what we call the soil horizons. If you were to dig down in the soil, you would go through a topsoil layer and a subsoil layer, et cetera. And these tells you the relative depth. So 0 to 6 inches in the A horizon, that's where you would expect to find them. The B horizon is between 15 and 25 inches and so forth. So this gives you the various depths of the different layers of soil, or what we call the horizons. And then here is a mixture of things that are variously important or not. For example, these happen to relate to the textures and the sizes of the ultimate particle. So, for example, remember we talked about sand grains are a certain size, or clay materials are a certain size. So this tells you the various fractions of soil that are in those different size classes. So you can identify, is it a sandy loam soil, or a silty clay loam, or is it a sand? All these are important to understanding sort of the textures and the composition of the soil from a material standpoint. Okay, now we're going to go to another table. Again, this is classic standard stuff that every soil survey has, really no matter where you are in the country. In this particular type, again, we're going to use the Kreider as our example. We have some general characteristics. Again, fine, silty, mixed, mesic, which means moist. You're going to hear that term mesic, by the way, a lot in this class. I think that's the first time we've introduced it. And I'm going to go ahead and write it on the board, M-E-S-I-C. We oftentimes will refer to a soil as mesic if it's moist. We refer to it as a forest as mesic if it's moist. And you will hear that pronounced both mesic and mesic. There's really no right or wrong there. Now we get next into a little bit of the classification, and this is the meat of what I'm going to tell you about today, is sort of dealing with this stuff. This is classified ultimately. I'm going to tell you about the major soils of our region can be classified into just about a half a dozen major orders, and this particular order is called an alpha sol. And we'll talk more about those later. Notice, though, that other kinds are mollisols. Why is that important? Mollisols are primarily a prairie soil. They particularly develop mostly under prairie conditions. Inceptisols are mostly soils of mountain slopes and hillsides. Okay. Alpha sols, though, are mixed. They can form under grasslands, they can form under savannas, they can form under woodlands and form under forest and in wetlands. So they're highly, highly variable. But this then sort of begins the jumping off point for understanding the major classification of soils. And we're going to get into this next. But let me see if anybody here in the class or online has any questions before we go into that. Anybody? All right. Soil classification of the soil orders. We're going to jump in on that real quick. So worldwide, no matter where you are, there are 12 soil orders. Think about these as kind of like, sort of like with plants, right, or animals. We've got kingdoms as a high level of classification. And then what do you have below the level of kingdom for plants and animals? What do you got? You got phylum, okay? Maybe this is actually probably more akin to phylum, it may be. What else is below that? Class. order, family, genus, and species, right? Similarly, with soils, we can go with order and suborder, supergroup, and all kinds of things, right? And we're not going to get into the fine level classification because, frankly, one, I don't know it. And it's really beyond the level of what we need to focus for this class. What I want to teach you here is to recognize the major groupings so that no matter where you're going, if you're driving across Georgia and Florida or Tennessee, and you see an exposure of soil, you can generally have a working knowledge to say, hey, that's an entisol or that's a mollisol, and here's why, right? Just very sort of high level is what we're keeping this. Now, for our region here, as I mentioned, there are 12 soil orders, but guess what? It gets easy because a lot of these aren't even in this region. We don't have to consider them. So for example, we have the two most common that you need to know around us are the alpha sols and the ultisols. We're going to go into sort of the general characteristics of these in a bit. Another important soil order, two others, are the entisols and inceptisols. Okay. And notice I'm putting these red bounding boxes here, kind of differentiate. Right? Those are four fairly common soil types for our region. Mollisols down here, which are grassland soils, but not exclusively. We do have soils on other types of grasslands can exist on different kinds of soil types. And then these two are exceedingly rare for the Mid-South, vertisols and histosols, okay? Do me a favor, raise your hand if you've had some exposure to soil orders before. Just raise them high. All right, a couple of you have, okay, good. All right, now there's a few things in here that I've included for your knowledge. So, for example, here are the same 12 orders. With this, there's just a very basic single phrase description. Feel free to study this. I'm not going to spend a lot of time on it, but for example, aridosols are the dry soils of deserts. Simple enough. Gelisols are soils that you would find in the Arctic tundra, where you have things like permafrost and frozen subsoil. Okay? So that's there for you to sort of study, and you can use those one-word descriptions. And this is a little bit more in depth. What I've done here is take away the soils that we don't have, like aridosols and andisols and oxasols, and I've focused on just the ones that we do have, the same ones I highlighted earlier. And then it's got a little bit more detailed information if you want to read that and study it and try to make sense of it, okay? All right, now what I want to do is let's go through sort of the, I'd say 6 soil orders that we have in this region that are important to know, okay? Now, with all these, what I'm going to do is I'm going to hit some key highlights. Number one, I'm going to very basically mention the map. I want you to visualize where these are. Maps are extremely important to our work and what we do. And I want you to visualize where they are and where they are not, each soil order. Secondly, we're not going to get into all this, the different colors. These are different kinds of alpha soils, and I'll explain that in a minute. I'm not going to read to you the description of an alpha sol, but that is there if you want to get into it and read it more deeply. Secondly, with each of these soil types, we're going to look at a general soil profile. That's what we call this. That's a photograph of a soil in cross-section, and we're going to talk about what the main features are. This is where I want you to imagine, right? Drive with me if you would. You're driving on a road. Hey, check it out. Hey, there's some soil over there. It's exposed. Look at that. You know, it's kind of brownish, but it's got a little bit of red to it too. And gosh, that looks like just some old nasty clay soil. I wouldn't want to bury a dog in that soil. I go back to burying dogs because I buried a lot of dogs in that day. Okay. Unfortunately, a lot of my dogs get run over and end up having to bury them in my front yard and backyard. And I know about, you know, the challenges that clay soil poses for that and planting trees. Okay? Oh yeah, but that's some brownish red soil right there, and it looks like clay. You know, Dr. Estes said that's probably an alpha sol. And I'll bet you one more thing, because we're in this basin, right, underlain by limestone. Limestone weathers into clay, and that soil gets all of its clay content, at least most of it, from that underground limestone. And what does that tell you about it? About the chemistry of the rock and the soil? It's probably what? It's probably not acidic because limestone is calcareous. Limestone's alkaline. That means it's probably high in calcium and magnesium and bases. So it's got a high, it's rich in alkaline elements, right? So all those things you can glean if you know what to look for just by driving 70 miles an hour down the road, bumping along, right? Now, I want you to generally be able to do the same thing with some of the common rock types, right? I'd like you to be able to look out your window and be like, hey, there's limestone, man. Let me tell you about limestone. Hey, mama, let me tell you about church. Hey, cuz, let me tell you about some sandstone, right? If you can think about how to do that with common rock types, the common soil types, and then guess what? You're going down the road, you're like, hey, that's a plain. I know, we learned what a plain was in 3rd grade. Oh, hey, that's a hill. If you keep pointing out landscapes to me because something Professor S is telling me, I'm going to lose my mind, right? What am I doing, James? I'm throwing out some rights. I need to pull them back. I'm going to pull those rights back in. So alpha soils, we're going to hit those in just a minute. Now, all soil types are classified. Each of the soil orders is classified into suborders. Now, we are not going there. Don't even ask me much about it, but I'm going to hit the highlights because there's some repeated patterns between each of the orders. For example, those alpha soils that occur in wetland environments, they put the prefix aqua in there to signify that it's connected to wet sites. So alpha soils that are wet are aqueous, okay? If they're cold, like think about cryo, like what is it? Cryogenic, isn't that where they freeze your body? Yeah. So if it's got cryo as a prefix, cryalphs are alpha soils that are very frigid and cold, like maybe you might see in parts of Siberia or Russia or New England. Then you've got these various other categories, like xeralphs are those that have a very dry climate like California or Italy or Greece. And then you can see these other ones like the eudalphs, which is the type we have around here. We have plenty of rainfall. So what structures the different suborders? It has to do with things like climate and moisture availability. That's what begins to separate those major categories. We're not getting into that, but I want you to at least have a working knowledge that that's kind of how soil classification begins to break down. Now, imagine that we took eudalphs, which are alpha soils that have plenty of rainfall throughout the year, which is what you expect here, right? Tennessee, good old Tennessee, you can expect rainfall most of the year in each month. So we have eudalph type alpha soils. But take a look at this. Eudalphs further divide into what we call great groups. I promise you, we're not going to ask you about great groups. Why are you telling me this? Because by gosh, you need to know. All right, and these are all kinds of great groups. And here's just a couple of examples of how they classify. So if you have a eudalph, which is an alpha soil with plenty of rainfall throughout the year, that has a salty soil, like Theo was telling us about the other, a pinch of salt. You see the prefix natru, which means salty. Then you have a natrudolph. Notice that it still retains that alpha from the alpha salt. If you have a fragiodolph, guess what? That's a soil that has a clay hard pan that is as hard as this table. Water can't penetrate through that. Roots can't penetrate through that. It's a clay layer underneath the ground about this deep. It's called a hard pan. Theo alluded to those as well, right? So you have a fragiodolph. See how we classify these alpha soils? It ain't that bad, but it is a lot of weird looking names, and it's a lot to remember. So we're not going there. All we're going to do is stop with reddish brown soil, clay, rich in bases like calcium and magnesium, can form under forests, can form under woodlands, under grasslands, in wetlands. That's an alpha soil. Very generic, very common soil type for this region. Now, I'm going to give you guys a couple of great examples of this website that I stumbled into the other day, which is cool. It's called Soil Web. You see the name up at the top, Soil Web. And after I get through going through this this lecture, I'm going to show you Soil Web and we're going to play around with it. But what you can do with Soil Web is you can look at anywhere in the country and you can find these mapped soil units And then you can click it and say, identify that, and they'll tell you what it is. So in this case, the Lawrence soil, that tells you the soil series, like Kreider we talked about earlier. And you got it up here at the top. And then guess what it does? It shows you a profile that you expect from that site. And so here's a cross section of the soil showing you the A horizon and the B horizons all the way down to the C horizon. And it shows you the depths. So the A horizon is from 0 to 25 inches. The B horizon is from 25 down to 157. Actually, these are centimeters. So, so 1.5 meters deep. This is almost 2 meters deep. And then all these different acronyms here, or the different letters, I'll show you what they mean in a minute. Again, all I want you to know is that you've been exposed to this and you know how to go back and find your way and navigate through this. Okay. Now, I'm going to promise you something. I didn't know jack shit about soils this time last week. Everything I'm learning right now, I learned last week. So if I can learn it and teach it, you can learn it, okay, and apply it. I'm sorry, I use profanity occasionally. Man, it's getting hot in here. Is it getting hot? All right, y'all bear with me. I'm gonna have to take this shirt off here. Try not to get too exposed. All right, all right. All right, everybody, it's hot in here. People are bound to get sleepy. It's after dinner time. You know, roll your arms around. We're gonna go about maybe 10 more minutes. We're gonna take a break, okay? It's making sense so far? Okay. All right, now, notice then also, there's some other links up here. I need a little bigger stick here. There's some other links up here which give you some useful information. You can click on Soil Data Explorer and Extent Explorer. All those will give you very useful but different information. I'll show you that in a bit. There's a lot of other kinds of things down here related to that soil description that prove to be very useful. Okay, so that's an alpha sol. Notice one last thing, and that's the color. They really try to be true about the colors that they're using in the profile. And so would you agree with me that generally speaking, the color that is used here is more on the brown side of things, or is it more on the red side of things? So it's a bit more on the brown side, right? Why is that important? Because ultisols, which are the other major common soil order for this region, are principally reddish and orangish soils. They have a red, more of a red hue, as opposed to a brown, more of a brown hue. That's a really important sort of base feature. All right. Now, I'm going to show you just some sites that are underlain by this type of soil. This is that exact site. In fact, this is called May Prairie State Natural Area. And it is considered to be an old growth prairie. This is considered to be hundreds of years old. And if you were to dig down, you would see that it has an alpha sol soil. Mollisols, which are coming soon, are thought to be prairie soils. Everybody talks about them being prairie soils. But it's interesting because we actually have lots of ecosystems that are grasslands that are not mollisols. All right, here's one more example of an alpha sol. This is out here in town near Google. This is a prairie that we are restoring. Ryan is working on studying this site. His master's thesis is out here. And so this is a site that if you were to look up here on the hilltop, that's an alpha sol soil. Again, would you think of that top layer as being more on the brown end of the spectrum or the red end?
Brown.
Yeah, it's a bit more on the brown side, right? It's not always easy to tell, but I think of that a little bit more brown. Again, alpha sol. Say it with me. Brownish side of the spectrum, clayey soils, also fertile because it's got a lot of nutrients in it, right? And it can be derived from pretty much any ecosystem. Think about those as your key factors. Here's that same site. The alpha sols are back up on the hill in the distance. Here's one more example, and this is Radnor Lake State Park in Nashville. Very hilly, lots of hills. This is a lake. And out here on the hillside, next to the lake, again, there's the soil sample taken. Again, brownish, rich in calcareous nutrients or minerals. Clayey, it's an alpha salt. And this is what that site looks like if you're on the ground. Okay, so very different. It can be forest, it can be open grassland. All right, now we're getting into ultrasols, right? Okay. So let's go back real quick and let's compare and contrast the maps of these two, because that's going to be directly leading into our next major topic of today, which are going to be ecoregions. Okay. So right away, I want you to see if you can describe to me, at least for the east. We're not concerned with, I'm still in ultrasols, right? Let's go back to alpha sols here. For alpha sols, going back here, I'm not worried about what's happening in the center and the west, but for the east, so pretty much from, let's say, the Great Plains east, are there any general trends that you can say, looks like alpha sols are kind of here or there? Anything stand out to you? At a large scale? Chase, do you have something? Oh, good point. So Chase is saying that maybe the sort of the flat to level terrains, right? So certainly a lot of central Kentucky is kind of rolling plains. A lot of West Tennessee is very flat. Okay. And to your point, you know, the heartland of the country is not known for being super hilly, right? It's kind of a gently rolling to lightly hilly area. Kind of follows the Mississippi Valley. Okay, Jacob? Mm-hmm. What is right in this zone here where there's not a lot of alpha sols here? Can you? Yeah, the Appalachian Mountains, right? So not a lot there. And then what's going on right in this zone? Anybody know? That's the Ozarks. Okay, so it's another kind of uplifted sort of mountainous or plateau landscape. Okay, now I want you to look at, that's at a macro scale. And now what I want you to do, and by the way, there are two kinds of alpha sols for our area, the aquifers, which are the wet alpha sols, and the eudolphs, which are those that are well drained and green. Again, I'm never going to touch that again. I just want to point that out. Now, let's look at a fine level, okay? So why is it, for example, that we see alpha sols really commonly here in this oval shaped region of Middle Tennessee, and we see it sort of in this sliver going up here and over there, and also in East Tennessee. But definitely there's these gaps in between. Why are the gaps there? Exactly. Around this oval region, which is where Nashville is, right? Nashville sits down in a big basin. We call it the Nashville Basin. And it is surrounded on all sides by this uplifted rim, the Highland Rim, which is kind of where Clarksville is, right? And other cities are on that rim around it. So we're elevated above. Notice that we don't really have a lot of alpha sols. There's some, right? Especially on the north side of Clarksville here. But by and large, these soils around are not alpha sols. That's important. Now let's go look at ultrasols and look at that map. Okay. What do you see with respect to the region around Middle Tennessee? It's the inverse, right? The areas that are now the upland highland rim or the top of the Cumberland Plateau are primarily ultrasol regions, okay? And then what can you generally say about ultrasols relative to alpha sols from a large scale distribution across the United States? What pattern? It's mainly the southeast, plus a little bit of the lower northeast, right? But it's really a southeastern soil order. Now, there were some other maps I could have included that show where these are on a worldwide basis. I didn't think we needed to go quite to that level. All right, now let's dig into the characteristics of ultrasols. Number one, at the top of the description over here, and this is for all the orders we're going to go over, there's a very general one-phrase statement. And that says that ultrasols are soils with low base status. Contrast that with alpha sols with high base status, right? High levels of calcium, high levels of magnesium, and other types of bases, or potassiums and those things. Here it's low in those basic elements. But they still, like alpha salts, have a clay-based soil. All right. So this means they're nutrient poor, they're clayey, they tend to be acidic instead of calcareous or alkaline. There's a lot of different things that you can just sort of do these direct comparisons. Because they're a little bit more heavily leached in nutrients, this means these soils tend to be not so much brown, which brown indicates more nutrient composition, especially more of your alkaline bases. But notice how red that is. It's more on the red end of the spectrum, right? That means it tends to be low in those bases. Here's a couple of more examples. Very much decidedly on the red, but if you can look, it's kind of blocky. You can see kind of where these shovel marks in here, right? Indicating that that's a clay soil. If you've ever dug in clay, you can kind of recognize it. All right, now, where do we find ultrasols? Again, we mentioned in this region, the Highland Rim, the Cumberland Plateau. If those terms are unfamiliar to you, don't fear, because that's what we're going to get into for the entire next lecture, is about the ecoregions of the region, okay? This happens to be an area that's on the Cumberland Plateau. Again, these soils, a little brown, but decidedly with a little bit more of an orangish reddish tinge to it, okay? Where do we find them? We find them in forests. We find them in savannas like this, scattered with grasslands and sort of scattered trees. We find them under woodlands, and in some cases also grasslands. Here's a site down in Dixon near Montgomery Bell State Park. This is one of the SGI grasslands that we manage in Dixon County. And so this particular area is a remnant grassland. Notice how reddish those soils are, right? And if you were to drive by and see these on the side of the road, so sites like this, it's underneath this grassland remnant, would have these kind of reddish clay-based acid soils, not basic, but they're acid. That's as deep as we get with soils, right? Very general, very much things that you can easily use. All right, let's touch on this next one fairly quickly. These are mollisols. Most people, if you say, hey, what is a soil that's associated with prairies, they would tell you this one. Why? Because the overall pattern is it's associated with the Great Plains, right? It's mostly western and central U.S. grasslands. And it comes into Illinois, which was formerly mostly a prairie region here. But notice that this map shows almost no mollisols in this region here, except a little bit down here in Florida, okay? But different maps show different trends. Take a look at this one. While sure, this one matches the previous map, notice that it gives a little bit more attention to Middle Tennessee. And notice that this is based on a relative percentage. The percentage of an area with 76 or more percent as a mollisol soil, right? There's only one or two places in all of Tennessee that have an abundance of mollisols. So if the supposition is mollisols formed from prairie, then we might suggest those were possibly former prairie regions, okay? But notice that if you were to look across the rest of Middle Tennessee and parts of East Tennessee, that there's a fairly light, occasional occurrence of these prairie soils. And what does all this mean? We're going to explore some of this as we go. But let's see what a mollisol looks like. How about that? That's pretty distinctive, right? These are dark black to very dark brown soils. They, what could you assume about its texture and composition? Imagine you were handling this with your bare hands compared to the alpha sols and ultrasols we saw earlier. What do you think? It looks like it looks a little bit like potting soil, right? It looks like you could just sort of crumble it in your hands, right? In the others, it looks sort of like a block that you just couldn't get through. But here it looks very, rich and friable is the word. And that's exactly what it is. These are the best agricultural soils in the world, or mollisols in some cases. That's why the Corn Belt of Illinois is the Great Corn Belt, right? And Iowa as a agricultural region. That's why the Great Plains are no longer the Great Plains. They're a bunch of crop fields because of how productive those soils are for agriculture. And they're very deep. very blackish in some case, and usually in some cases. And here's a couple of examples to that. There are exceptions. This one kind of is not as deep and grades into sort of a lighter gray, kind of a subsoil. This one, that dark is not so much black as it is very dark brown. And notice here that it begins to grade into a sort of a chalky subsoil or a clay-based subsoil. So sometimes that black friable soil is very deep. It could be several feet deep. It could be a few meters deep. In other cases, it may just be a few inches deep. Typically, the mollisols of this region tend to be more on this end of the spectrum. The mollisols of the Great Plains, where prairies have been for, a few thousands of years, maybe tens of thousands in some cases, you've got layer after layer of old grass that builds up and forms this organic rich element that sometimes can be a couple meters thick of very rich black prairie soils, as they're often called. Here's a place in Tennessee. This is down in Nashville. This is one of the prairie restoration sites that SGI works at. This entire large bottomland here, which is part of a city park called Lytle Bend Park. The Nashville airport, by the way, would be about where the floor is. That's how close it is to the airport. This is a large site. It's part of an 800-acre city park we're restoring with the city of Nashville and the Nature Conservancy. And I'll show you a picture of that. But this entire bottomland, all around through here, is all mollisol soils. And if you were to go up a little bit higher, this terrace here has a different type of soil. It's an alpha sol. If you go still a little bit higher, this back in here is an ultasol. And there's actually even another one back in there, which is yet a different type. So this is an example of where you get a large sort of prairie type soil right here. And it's the common place for it. In Middle Tennessee, we often see mollisols in our larger river bottoms. And that's kind of strange because that sort of goes against what most people thought these river bottoms historically were forested. But maybe, in fact, they were open. We'll get into all that later. But this is one place you would expect mollisols is in your big river bottoms, some of your stream bottoms. Now, here's another case. This is another site that we at SGI are managing. This is about an 80-acre wet grassland that we're restoring near Murfreesboro. And if we were to go into this site, this is sort of a basin. It's a flat part of the Nashville Basin. You can see there's little rises over here. It's wet, so it holds a lot of water. But these soils are really black, and when they're exposed, you see that. So we get mollisols both in floodplains and in basins, especially that are wet. And there's one last place that we get them. This is actually nearby to this site. You see off in the distance for all these red cedar trees back in here? That indicates it's real rocky. And there's some limestone near the surface back there. And where you have that, in this soil type called GRC, you can take a soil sample there. Here you can see that the mollisols are very dark, but they're only pretty shallow. They're only down to about 25 inches at the very most. What's underneath that is right here. What does that say? What does that signify to you? Yeah, the R layer, when you're talking about soil horizons, the R is the bedrock layer. Yeah. And in this case, it's limestone. So a couple last attributes, and that's what these sites look like. Here you have a very shallow soil layer overlying limestone. The soils are so thin that trees can't really grow well. So trees that might need to put roots down below 25 centimeters can't. And so instead of a site being maybe favored for the growth of trees, it instead favors small herbs and grasses that don't need quite as deep a root system. So this is an example of a type of natural rocky grassland we call a glade that has mollisol soils. Okay. All right, let's talk about one other major soil order. This is called a vertisol. Vertisols for us are very rare in the Mid-South region. We have them out here on the floodplain of the Mississippi, and we get them in places like Mississippi and Alabama here in the sort of crescent-shaped area. And by the way, that's a region called the Black Belt Prairie region, as it's known. And it gets its name because of the very dark blackish soils but they are not mollisols, they are vertisols. And I'm gonna explain the key difference in a minute. Now, notice here that these prairie soils here, these vertisols, are also found down here. That's another type of grassland region. And then they jump over here and they're found along the coast of Texas, up through San Antonio and Austin and Dallas and Fort Worth. And collectively, these prairies plus these soils here are all known as the blackland prairies. So if you ever talk to somebody in Texas and they'll say, yeah, our farm is out in the blackland region, that's because these areas have very dark blackish soils that are about the color of the base of this screen. And you can see them when they plow the soils in March and April. Those soils are as dark as the tabletop. And you can tell those are very fertile, very rich. And part of the reason why they're so black is that they have a very high organic carbon, amount of carbon stored in the soils. But what's the key difference between a vertisol then and a mollisol, which is also black? Well, it happens to do with the texture. Okay, notice then, if you're looking at this, you see how blocky it appears to be? Let me darken this room just a hair. See how blocky that is? And that's because these are extremely clayey soils. They're black clay. And sometimes they're even called gumbo soils. When they get wet, have you ever walked in a clay area with tennis shoes, like a construction site? And what happens is the clay sticks to your shoes, and what does it do? It builds. Eventually, you just kind of like lifting your feet. And it's like giant clumps. It's almost like you're walking with snowshoes, right? All that clay is building up and it just sticks. Well, imagine if you're early settlers and you're crossing the plains of East Texas and you're going through in the springtime, try to find a place to settle. You're crossing the blackland prairies in a wagon. These areas can be very difficult to traverse and cross, and they were major impediments to early travel. Huge headaches for roads, farming. You can't really plow vertisols very well in the wet season because they just kind of gum up. That's what they call gumbo soils. But then, just in the same way that they get super wet and sticky because of all the clay, they also get hard and they dry and they bake in the summer sun. Think about that Texas heat. Same heat in Arkansas and Alabama. It just gets ferocious in the summertime. So what happens is when those soils get a lot of rain, they swell, right? And then when they go through drought, they shrink. And what that ends up doing then is causing a lot of these sort of cracks to form through the soil. And you can see it just like that. These are called shrink swell soils. And they're very important for natural, what we call understanding the natural environment, natural history. And I want you to tell me why as I plug my laptop in so we don't die here. What are shrink swell soils? How could they sort of control the vegetation at a site? The type of ecosystem that is at a site.
Bugs down there.
So you mentioned a really good point. You said sort of almost like a natural tilling of the soil, right? This shrinking and swelling is like it's almost acting in place of a tiller, right? It's sort of bioturbation a little bit. Remember that term we talked about where animals are sort of helping to turn the soil over? But in this case, it's the mechanical contraction and expansion of the soil, which is helping to work the soil out. And as it does that, some elements are sifting down and other elements are getting pushed up. And what it's doing is it's sort of slowly over hundreds of years, churning that soil, mixing. Okay, so there's a natural mixing effect that comes into play there. That certainly is important, but also important here in terms of what kinds of plants can grow and not grow in a shrink swell soil. Jaron? Why is that? Okay, that's good, right? So imagine you got a tree, a young tree, and it's growing in this pedon, And then it puts out a taproot that branches over into this pedon. And then that soil, as it's moist, right, it grows right through with no problem. But what happens when it fractures and it dries? And then that soil shifts and moves. It could shear those root systems, right? So you could have a tree here that's say 2 feet tall, a young sapling, that then becomes completely desiccated and dry because its root system essentially it'd be like taking a shovel and just putting it in the ground all around, right up against the base of that tree, shearing its root systems, killing it, right? From the effects of drought and the effects of this cleavage of its root system. On the other hand, grasses and herbaceous plants are much better able to withstand the shrink swell effect. So take that out over years or decades or centuries. What kinds of ecosystems are favored on vertisols compared to non-vertisol soils? Grasslands and savannas, particularly prairies, are favored in areas of vertisols, okay? Now, here's an extreme case of vertisols down in Texas. And you can see there that shrink swell effect is pretty real. And it has a very dramatic impact on the vegetation and on agriculture. One of the common sort of features of a vertisol soil is what's called a slicken side. Sounds like somebody just was trying to be cute, you know, and come up with that. But in reality, what it is, it's sort of like these smooth clay areas where you can see them as you dig into the soil. It's like a clay wall. And those are a unique feature of vertisol soils. Now, as we look here, I just want you to notice how blocky they appear to be, right? Very blocky, extremely blocky with vertical cracks, kind of blocky and angular overlying chalk bedrock here on the right. Okay. And then where would you find them in our region? Just to recap, again, in this particular case, this is the Black Belt Prairie of Mississippi and Alabama. Notice the soil profile, very dark, blackish soils, differing from mollisols because they're so so blocky and fractured. This is what a black land prairie landscape looks like. And then here's that heaving effect, that turnover of soil that we talked about. See that? Where you've got this sort of natural mixing of soil just by the shrink swell effect. And then the final place we expect vertisols, look how dark and black those are. This happens to be in the floodplain of the Mississippi River. This is Reelfoot Lake, if you know where about that is, north of Memphis. These are some really deep swamps right here. And those swamps are developed over clays of the river bottom that are very deep and very black, very clay, but normally they're waterlogged. But if they ever dry out, then they have those same shrink swell properties that we talked about. So vertisols are in prairie landscapes and in swampy river floodplains. That's where we find those two. And that's kind of what the area looks like with the vertisols there. This is the part of southeast Missouri, right across the river, where the vertisols have been, where the forest has been cleared and drained. And you can see the resulting black soils here that are being used for agriculture. So quick question again, Kiki, how would you differentiate vertisols from mollisols in this setting if you were walking around out there in the field? Okay, anybody? Anybody want to help out? Matthew?
Right.
So remember, they could be similar in color, right? They could both be black. These are going to be very clayey, very fractured. They're either going to be very wet and sticky and gumbo, or they're going to be fractured and cracked, right? Mollisols are mesic soils. They're pretty much always kind of moist. Certainly they can dry out in a drought, but they're friable. You could break them apart, right? They're not heavily clay-based. Part of the challenge of this class, and it's part of the thing that I'm going to have to be mindful of how to deal with, it'd be great if we had a sample, right, of vertisol and a mollisol. We're going to develop that in time, but right now you just kind of got to go with me. One is inceptisols. Basically what an inceptisol is these are your common soils of slopes of mountains and steeply sloping hills. These are thought to be young soils. Okay, they are also poorly differentiated, which means that if you start at the top, at the surface, and go down through the topsoil, what we call the A horizon, into the lower levels, in this case, you have just sort of a couple of pretty obvious distinctions here, right? That looks different from this, but there's not more than that. If you were to go back and look at some of these other types of soils, oftentimes there's repeated profile changes. Inceptisols are so young that they haven't had the kind of time and duration to really establish multiple levels of different kinds of soil layers or different profiles. Okay. So where do we find them? Again, steep slopes above a river, for example, here in the Blue Ridge Mountains, down around the Ocoee River Gorge. Places like Great Smoky Mountains National Park, a lot of those slopes will be inceptisols. Here in Middle Tennessee, this is Cheatham Wildlife Management Area, some of the steep slopes of ravines. And generally, these are kind of, in terms of color and appearance, they can be very similar to either alpha sols or ultrasols in some cases. A lot of these slopes here, Beeman Park down near Nashville, would be inceptisols. All right, and then the last category, which is a very easy group, are called intisols. And intisols mean soils that are recently formed. These are the youngest soils that we have. Notice that they're scattered all across the country without any sort of clear pattern. And those in the east are primarily associated with a couple of environments. Number one, notice that you've got a lot of them along the lower Mississippi River and some of the larger rivers here in West Tennessee. That's because of sort of two factors. One is soils that are laid down along a river floodplain. So if a river floods and it deposits a layer of silt, that's a very young sediment layer. That's an intisol, a recent soil. If you have areas out here where you have windblown deposits of sand, like the sand barrens of Wisconsin, the sand hills of Central Florida, the sand hills of South Carolina, these are very young, sort of, not always young, but they're just poorly differentiated, often a single layer, but they are oftentimes young as well. So here's where we see those, like this. Almost no differentiation, just a sand dune here in the Nebraska sand hills, for example. That's this big patch of orange right there. In this case, we have, this is an area, where is this from? I'm not sure, but it's basically a very deep sand dune. Notice there's almost no profile development of different A layers and B layers. It's all sort of very even. And then here, this is a riverine deposit in a floodplain. So very recent soil, just a little bit of differentiation at the top, not a lot in that case. Okay. So where would you find them in our region? Here's the Mississippi River. Right alongside the river, you would find these intisol soils, very young deposits. Closer at home, and this is what those look like right here adjacent to these sandbars kind of up here on the edge. And then closer here to home, you would see them, particularly in places like down south of Clarksville, where you have a lot of these rivers that have gravelly floodplains and gravel bars, great fishing rivers. These are the rivers, though, that like when Waverly had the big floods a couple years ago, those floodwaters get out and fill this entire valley. That's why it's so dangerous in times of high water. You'll see counties that'll let out their schools because school buses can't go down these roads because there's so much flooding of driveways and county roads. So these will readily flood over their banks. And then what happens is all the gravel gets shifted and reworked. And so that gravel bar may be there in 2018, but a giant flood comes in 2019, and then it can obliterate that gravel bar and move it, and it might not be there that next year. So that gravel bar gets redistributed and maybe deposited here on this floodplain, for example. So those are what we call intisols. All right, so hopefully that makes sense. Here's a quick picture of where you might expect those. Notice those gravelly banks on both sides. There's one last type. Of course there is, Professor Estes. You always undercut. You always say you're almost done, but then you're not. You keep going. We go to one last category. By the way, this is a rare type. Do you see any in the Southeast? Well, at least in our Mid-South region here. There are none mapped, although there are some known histosols out in Henry County, just over the Tennessee River. There are some in various places, and I'm about to tell you about one here in the mountains of North Carolina. Why are they important? Histosols. Well, does that prefix histo mean anything to you? What does that sort of remind you of? History, what else? Think about human anatomy and physiology. Histology, which is what? Tissues, structures, right? Think about like organic materials, right? Living, parts of the living body. What histosols are soils that are primarily composed of living plant materials that are poorly differentiated. So instead of clay or sand, these are actual plants that are poorly decomposed. Let's take a look. In this case, here you can see that top layer is sphagnum moss, what we would call peat moss if you bought it in a store, right? Normally, though, we're buying something that's a little bit more decomposed than that. That's almost like true sphagnum. You can see it when it's in this stage, it's in that fibric stage. You can still make out the moss leaves and the stems, okay? That's still very much identifiable. It hasn't gone through much decomposition. The farther down in the profile you go, though, you get partially decomposed material where some of it's still evident, but some of it is undergone decomposition. And that's called hemic material. Hemic being hemispherical or half, right? And then you get down to sapric, which is a very advanced state of decomposition. And in this case, these are really slick, almost like satin, and kind of like a very nice film. But all of these have in common that they are organic soils almost entirely. Sure, there might be some sand grains in here and some pieces of minerals, but by and large, these are derived from poorly decomposed plant matter, especially mosses and other things. You can find in sapric materials, though, pine cones and spruce cones and pieces of tree trunks. If you're in Ireland or Scotland, you can find people buried in these things. Have y'all seen that in some of your textbooks? Where they've retrieved whole mummified bodies from bog deposits in places like Scotland, for example. Now, we're going to come back to this classification when we get into wetlands, because when we start talking about bogs and certain types of wetlands, these soils become important. So what's the last couple things we need to know about histosol soils? Number one, because they're so organic rich, they actually have another layer at the surface called the O horizon. That's a very organic rich layer. It's almost no soil. It's almost all organic content, plant matter. And it's black or very dark brown. Now, below that, this is all waterlogged. So these are wetlands, always, pretty much. And for that reason, you expect these soils to be along small streams or in flat areas among mountain valleys. And this is called Long Hope Creek in North Carolina, near Boone, North Carolina. And this is what that looks like. You've got a little creek that just sort of winds its way in this flat valley bottom where all the water just sort of sits. And it has sat for thousands upon thousands of years, leading to these organic soils. And right in the middle of that is one of the rarest ecosystems around, home of the endangered bog turtle, which is found in these little open peat bogs surrounded by spruce trees. It's almost like a little bit of eastern Canada in the mountains of North Carolina. Let's talk about just a brief recap of horizons, and let's remind ourselves of where we are. Before we got into all those soil orders, we were looking at the soil survey document, right? Which we said is an important tool for people studying ecology. Let's go back to that soil survey document. And here we're back in that Kreider soil series, which is our example, okay? And then you'll notice within the description, it provides the breakdown by profile. And what I want you to notice is how you can use that to understand what's happening in the different profile horizons over on the left. So your A horizon, shown here, it's below the O horizon, the organic, from 0 to 7 inches. And then you've got a number of things right there that I want to help you to understand where that comes from, okay? So first of all, sometimes there's a term that you'll encounter. We're not going to spend a lot of time on it. We call it epipedons. That prefix epi means upon. So it's a layer that's upon a pedon. And in this case, all it's saying is basically you can have a dark layer on top of your pedon. And sometimes it's thin and sometimes it's thick. And those you just need to know can complicate your soil analysis. So sometimes you can have what's called a molic epipedon. That's a thin layer on top that is essentially a mollisol, a thin mollisol layer. All right. So let's get back into this here. We're talking about how to sort of understand some of these basic concepts in here. Number one, at the A horizon, you'll notice that there's a lot of letters that are accompanying each horizon layer, right? So notice that there's a T here and there's a P. In this case, the A horizon, that top layer, the top soil, if we go down and look at this, we can see that's the master horizons. Let's go to this chart right here. That P means that there's usually a lot of disturbance at that layer. P means it's plowed. In most cases, it has been subjected over the past 150 years to plowing. Okay, that's what that P refers to. Next thing we want to look at, and there's a whole bunch of these I've included. So there's like a KK, for example, has a certain meaning, or a V. These all mean certain things like certain minerals that are present. All these kinds of factors are helpful for classifying soils. It's a little deeper than what we want to go, but I've included them here for your information if you want to seek that. The second thing then that, or the next thing we want to get into, after we've addressed how deep it is and we understand what that P stands for, let's look at the coloration here, right? Now, colors are hard to quantify. Would you agree? I mean, they're subjective in some cases. They mean different things to different people. Some people may not have good eyesight. Some people may be colorblind, right? In this case, though, color is quantifiable as a characteristic, and we can apply that a numerical color class. And so this is very commonly done by people, especially who study wetlands. Have you ever heard of a Munsell soil chart? I'll show you what that is. So number one, this code that you see, 10YR43, this happens to be a numerical number that involves three things. One is what's called the hue, which is this sort of circular set of characteristics here. Basically, the hue of a soil is it generally a yellow soil? Remember how we were talking about alpha soils tend to be brown, right? Is it tend to be a little bit more of a brown type, or a red, or a yellow, or sort of a greenish soil? That is your hue. That's sort of your first level of classification of soil color. Secondly, then, you want to look at the value. And this is relatively from dark to light on a scale of 0 to 10. If it's very dark, like a mollisol, it's going to have a value of something like a 0. If it's very light, and maybe it's a calcium layer that's bright white, it might have a 10. Okay? That's its that's the light factor from dark to light. So general colors is hue, okay? Dark to light is its value. And then the brightness, the intensity, I shouldn't say brightness, the intensity of that color. So think about, for example, which one of these is more intense as a red? Which one's more vibrant? Which one's more dull? This one's more vibrant? Right, what do you guys think?
The light.
It does have a light going through it. All right. I'm going to pass it around here. So one's a bit more dull, one's a little bit brighter. What do you think? As a red, that is. And you don't have to wait till it gets all the way across. Somebody can just spit out an answer and then I'll tell you if you're right or wrong. We'll let it go through just a minute. Now, so I want to bring this back to, God, Dr. Estes, why is this important? Well, because I have known my fair share, probably a dozen or more, people who were in a biology program, getting an ecology degree, they get out of school, intent on becoming PhDs or whatever. And then at least half of these guys and girls have gone into environmental consulting, right? They go work for an environmental consulting firm. And then as part of that job, they have to do a lot of stuff. One of which is regulation of wetlands. They have to identify wetlands as for part of their work, right? And as part of that, one of the defining characteristics of wetlands involves looking at wetland soils. And you have to use what's called a Munsell soil chart, which I'm about to show you. And it involves identifying the color of the soil. Why? Because certain soils that are wetland soils have a certain numerical value. They have a certain code. Whereas upland soils that are non-wetland soils have a totally different value. Okay. In this case, all I'm wanting to do is introduce you to these concepts because they're important as descriptors of soil, and because the soil color conveys certain information about soil properties. So, for example, if you've got grayish soils that have flecks of rusty red in them, you can be sure that you have soils that are waterlogged. So whatever value that is going to be in the grayish end of the spectrum, and it's going to tell you something about those soils. If you have soils that are red or yellow red, that probably tells you you've got a lot of iron composition in your soils, right? Certain types of mineral composition. All right, any thoughts on the intensity here? Which one's more intense, more vibrantly red? The box, yeah. So in this case, the chroma, which is that last value, would be higher in the red box. The one that's duller, in my opinion, is the bulb. Okay. Now we can use this with a standardized system of color plates, which we can get with what's called a Munsell soil color chart. And this is the book that you can buy. It's actually about $200 or $300, and you can flip through it. And if you have a piece of soil, you can put it behind and sort of compare and match up based on which soil coloration best matches. Now, you'll notice I've included a link here because I'm not going to walk you through all this stuff and tell you exactly what's what. But I would encourage you to watch this. If you think you might go into a job working for, an agency or working as a consultant, you may very well find yourself doing some of this wetland classification stuff in the future, which is going to really depend on you using these manuals. But in essence, this is the way you can kind of identify those. And you'll notice then you have your chroma score down here, you have your value score over here, and this is your main sort of color pattern. Is it a yellow-red color pattern? Is it a green color pattern? Is it gray? So by doing that, by lining all three of these up, you could find the best match. And then that tells you your specific color. So maybe you have something that's like a 10YR 5-3. Okay. So if you go back here, 10YR 4-3, that's how we get that number. That's where it comes from. And to me, if I were to have just read that before last week, I didn't know what the hell that meant. I didn't know where it came from or what it was trying to say. Now you've been exposed to it, and now you can dig deeper if you need to, especially as you get into this field. All right, just a few other features here. Now, another key element, in addition to soil, the soil color, is now the soil texture. Okay, I'm trying to boil down a lot of complexity as simply as I can, but let's say, for example, again, this is in every soil manual. Here's a description: silt loam. What does that mean? It means something very precise. Us scientists are very precise. Here's how we get that. Silt loam, and by the way, there's a link to a video here for how specifically to determine whether something is a clay loam or a sand or a silt loam or any of these other sort of dozen categories, right? Here's how you find out. You have to, you can follow this and go through a key to actually identify that soil. essentially what you're looking at is to see how much percent clay would you estimate your sample has. You're using a little, sort of a little ball about the size of a quarter. How much clay does it have? What percentage? How much silt does it have? How much sand does it have? Then what you do is you match that up. You say, I think it's got 10% sand. It's got 90% silt, right? When less than 10% of something else, actually that's a little bit here. You find the junction point of where all those come together. That math didn't quite add up, but you get the point, right? But it would be classified then as a silt line. Why is that important and why is that helpful? Because of this reason. If you're looking at ecosystems, lots of species only will inhabit sort of clay-based ecosystems. Gopher tortoise, for example. Anybody know anything about that reptile? Is it like sand or clay? Yeah, gopher tortoise digs. It's a keystone species in the deep south. It burrows down into sandy soils. So, it's not going to burrow into clay. It's probably not going to burrow into any of these. It's going to burrow into something that's either pure sand or probably a loamy sand or maybe a sandy loam. But probably it's going to be one of these two right here. That species then makes these burrows, which attract eastern diamondback rattlesnakes and burrowing owls and so many other species. And so it's a keystone species for a whole ecosystem. We could give countless examples of other species that are associated with particular types of soil types. So this texture analysis, which is in the soil description, and remember, we're mapping the crider soils. We've already shown you how to find that on the map. This is just trying to make sense of how exactly what does silt loam mean. It means this. It means it has this much silt, clay, and sand that comprises that soil sample. Okay? All right, just a few other factors here. Soil texture, those are all over the board. They range from granular to blocky, all these kind of things. We don't have to get too far into it, but you can see that right there in the description. Granular structure is part of that description. Friable basically means it's very easy to break apart with your hand. All right, one last characteristic here of the description is, and there's some of the different structures there that we just pointed out. The last one of the description that's important is the pH. Okay, and there's various pH meters you can use to differentiate this, and there's several categories, all the way from ultra acid to very strong alkaline. You can see the pH breakdown. pH is one of the best predictors of where plants grow. And if you can predict where a given species of plant grows, or a whole suite of species, then guess what you can do? What can you predict if you know the plants? Yeah, if you know the acidity, you can pretty well know what plant's going to be there. But if you can know what plant's going to be there, what can you predict? What animals, right? If you know the flowers are going to be there, and those are the wildflowers that are producing flowers, then you can predict which pollinators will be there. If you know which pollinators will be there and the structure of those plants, you can determine whether or not a tall grass prairie with grasses and wildflowers that are chest high is going to support Henslow sparrow, a tall grass prairie species. But it won't support a grasshopper sparrow. Why? Grasshopper sparrows have to have short grass down here, ankle high, no more than mid shin high. They have to exist mostly in short grass prairies. We don't have short grass prairies naturally in Tennessee anymore. So what are the closest things to a short grass prairie? Pastures. Yeah. So if we're going to have restored grasslands and we want to track the very rare grasshopper sparrow which is collapsing across the nation, we need to make sure that we're building the prairies back in the appropriate soil, right? With the appropriate plants so we can attract the right animal species. And then we need to know about the appropriate management. If we bring in a prairie and restore it, but we don't bring in something to knock the grass back periodically, at least in places like bison or fire or cattle, then we're never going to attract grasshopper sparrows in that grassland again because it doesn't have the full complement of what it needs. All right, I think with that, let's see. We're gonna call it done on soils. There's a few additional slides in there, but they're things that I can cover easily in future lectures on other topics.